Good morning, everyone. Okay, so in this session, this 1 hour session, we are going to see what does asymptotic analysis mean. Given an algorithm, how do we analyze that algorithm, and what are different asymptotic notations. Okay. And whatever material I have taken, this is from these 3 textbooks. Okay, this is content. It is very simple to read and understand, and this is standard textbook for algorithms. So, whenever we say problem in engineering domain or anywhere, okay, so it means what type of problems we consider. It is not how to become rich in 5 years or how to remain happy forever, not this type of problems, no. So, whenever we say problem means it is a computational problem. So, what does computational problem mean? So, there is some computation or calculation involved in it, and we want some computing device like computer to solve it for us once it is told how to do it. Okay. So, that type of problems only we consider. Can you give an example for computational problem? Anyone of you? Given a number, natural number, find factor it into primes such that product of that primes is given number, or simply given a natural number determining whether that number is prime or not. Okay. Any other? Satisfiability problem. Yes, there are so many optimization problems. No, that also you can go. Traveling salesman problem. That is also a computational problem. No, simply these are different examples for computational problems. Okay. Any problem, computational problem, first we need to formally define that problem. So, hereafter whenever I say problem means it is a computational problem. Formally define the problem. Formal definition of the problem means we need to clearly say what is input and what is output. For example, all of us are familiar with sorting problem. So, what is input in case of sorting problem? A sequence of n elements. Okay, A1, A2, A3 and so on we can call AN. What is output? What is sorting problem is we should not say sort it, no. Yes sir, thank you. So, it is reordering of that n elements. Whatever n elements are given to us, we need to reorder that n elements such that it should satisfy some property. If input is A1, A2 and so on AN, n equal to 4 if I take, input is say 10, 15, 12, 8. If input is this, then what is this? I call it as A1, A2, A3 and A4. This is input. Then what is output? We know that output is this 8, 12, 10, 12 and 15. This is output. Now, this I can call it as A1 dash, A2 dash, A3 dash, A4 dash. But what is this? Can I say that it is reordering of given 4 elements or a permutation of given 4 elements? But what is the condition that permutation is satisfying? The first element is less than or equal second element element is less than or equal third element and so on. Okay. Can you say something like this? That is input and output. Input is a sequence of n elements A1, A2 and so on AN. Output is a reordering or a permutation of this sequence of n elements A1 dash, A2 dash and so on AN dash, such that A1 dash is less than or equal to A2 dash, less than or equal to A3 dash and so on less than or equal to AN dash. And this ordering is called, is it a decreasing order or non-increasing order? Or increasing order or non-decreasing order? Non-decreasing order. Increasing order and non-decreasing means next element may be same as previous element, then we say that instead of calling it is not increasing, no. We say that non-decreasing. In textbooks they use this terminology, no, non-decreasing, non-increasing something. Okay. Now, what are the specific values we give as input? That we call it as an instance of the problem. So, here these are the specific values we give as input, that becomes an instance of the problem. How many values we have given as input? In this case 6. That 6 we call, loosely speaking, we call it as input size. But actually what is input size? How much memory is required to store the given instance or given input? How many bits of bits are required to store this given input. Okay? But we are not going into the details exactly. How many elements are given, that much we consider it as input size. Okay? Input size here it is n. If you are given n elements, n. Here in this case it is 4. Okay? What is input size in case of any matrix addition problem? You are given 2 matrices, you need to add the 2 matrices. What is input size? Number of rows as well as number of columns. Input size can be 1 parameter or it can be more than 1 parameter also. Okay? If it is a graph related problem, what is input size? Can you simply consider only number of vertices? No. With same number of vertices, we may have different edges also. No. So, input size is number of vertices as well as number of edges. Input size is only 1 parameter, it is denoted by n. Okay? And this word algorithm, it has come from the name of Al-Khwarizmi, who is considered as father of algebra. Thank you very much. He is considered as father of algebra. Why his name only? We know this is definition for algorithm. Different textbooks, they give different definitions. It is a step-by-step procedure for solving well-defined problem or a sequence of computational steps which transform input to output in finite amount of time. Okay. So, he was the person who has systematically given procedure or step-by-step procedure for solving linear as well as quadratic equations. Okay, no? And one of his books, it was translated into Latin. In that Latin, they also translated his full name, Abu Abdullah Muhammad ibn Musa Al-Khwarizmi. That entire name, they translated as algorithm. From that name only, this word algorithm has come. Okay? Now, any algorithm, you know that it has to satisfy these 5 properties. Okay. Out of this, we discuss what is finiteness property. An algorithm must satisfy finiteness property. What does it mean? It does not mean that number of lines in the algorithm is finite. Here 4 lines are there, then we cannot say that algorithm has finiteness property. Because there are only one line, step 1, step 2, step 3, step 4. Can we say that this algorithm has finiteness property? No, it is not number of lines. Then what is finiteness? Here there are 6 lines. What are those lines also not mentioned? Can we say that, oh, total 6 lines are there, this algorithm has finiteness property? No. Then what does finiteness mean? It is total number of operations performed in the algorithm for given input size. That value we need to calculate. If that is finite, then we say that our algorithm has finiteness property. Okay, let us see. In order to understand, we have written an algorithm to solve a problem, computational problem. Then this algorithm we need to know on what type of computers you are going to whatever program you write, this algorithm to program we convert, that program on what type of computers we run it. That we need to fix now. It is like if I ask Scooty, okay now, what is the mileage it gives? What are the answers? Some people might say 40 kilometers per liter. Some people might say it is, if you are riding it in highway, it may be 50 kilometers per liter. Or if you go to Rajasthan, Thar desert and you ride it, then it may be 10 kilometers per liter. Same person is riding the scooty, but depending on the underlying conditions, the amount of time it is taking is changing. No? Similarly, here also, depending on what type of computers we are going to run the corresponding program, the amount of time this algorithm takes is going to change. For that, first we need to fix on what type of missions we are going to run this. The model that we use is, the simplest model is, it is RAM model of computation. What is RAM model of computation? It is that type of computers, they have only one processor, okay, no? Single processor. And one more thing is, they have infinite amount of memory, and irrespective of physical location of the memory, all elements we can access in same amount of time. That is called random access, no? That is random access. All operations also take same amount of time. Whether it is addition, multiplication, division, subtraction, they take same amount of time. But is it actually correct? Multiplication is repeated addition. It is supposed to take more time than addition. But here our assumption is all operations take same amount of time. Mainly only one processor, no parallel execution, all operations take same amount of time. If you write any loops for I equal to 1, I less than or equal to n, I plus plus, something like that, they are not considered as single operation. It is a collection of operations. How many? That depends on that for loop we can calculate. Is that okay? under RAM model of computation, our assumption is RAM model of computation, there is only one processor, no parallel execution, infinite amount of memory is available, memory access is random. All operations take same amount of time, but the function calls and loops, they are not considered as single operations. They are some sequence of operations. Is that okay? Random access machine model. Okay. For example, in memory, irrespective of its data is stored in memory, irrespective of its physical location in the memory, we should be able to access that item in same amount of time. Whether it is starting or ending, it doesn't matter. Memory, that means irrespective of its physical location, we access in same amount of time. Okay. That is called RAM model of computation. Under this model of computation, what is running time of an algorithm is total number of steps or operations performed in this algorithm. Okay. Okay, even if it is not clear also, okay, next step it will be clear. Okay. Now, this is an algorithm, there are say 8 steps in this algorithm. Okay, what are the steps I haven't mentioned? Let us suppose that in the first step, we are performing addition operation. Here, whatever line, okay, addition operation. In second step, multiplication. Like that, all 8 steps, what is the operation that is performed is mentioned. Here, there are some mathematical operations, some logical operations like that. Okay. Now, when n is input size, how many times this addition operation is performed in step 1? That is denoted by, say, letter T1 of n. In second step, multiplication operation is performed. How many times that multiplication operation is performed in step 2? That is denoted by T2 of n. What does this n denote? Input size. N is input size. Like that, there are 8 steps in our algorithm. Each step, you write down how many times that operation is performed. Then take summation overall. T1 of n plus T2 of n up to T8 of n. What is that we get? Total number of operations performed in our algorithm. It is nothing but operation count. Total number of operations performed in our algorithm when n is input size. Okay? And that operation count only, loosely speaking, we call it as running time of that algorithm. Is it actually time? Running time means is it time? No, it's not time. It is total number of operations performed in that algorithm. But why addition and multiplication I am considering it as same? My model of computation is RAM model of computation. Under that model, there is no difference between addition and multiplication, subtraction and division. Actually, that is not correct. But we use our RAM model of computation only for understanding how much time our algorithm takes. Is that okay? Okay. Then this is called operation count. That is only we call it as running time of that algorithm. Okay. Now, what is running time of this algorithm? What is running time of this algorithm? So each step similar to the previous whatever I mentioned, you can write what is the operation performed in each step. For example, step 1. So what is the operation performed? Operation performed and number of times. Operation performed is assignment operation. Can you say that it is assignment? How many times that operation is performed? Only one time. That means here T1 of n is 1. Is that okay? How many times this operation here? It is not one operation. Loops are not considered as single operations. They are collection of operations. What is the operation that is performed here? Here it is actually like this. For I equals to 1, I less than or equal to n, I plus plus. It is like this now. Here we are performing increment operation, comparison operation. 2 operations we are performing there. Okay, let us count 1. That is. So let us say that we are performing some comparison operation. How many times comparison operation is performed here? How many? N or more than n? If n equal to 4, how many times comparison operation is performed? Exactly. N equals to 4. That means our array contains 4 elements. When array indices are 1 to say 4. Array indices are 1 to 4. Array indices are 1 to 4. When I equal to 1, comparison happens. When I equal to 2, comparison happens. When I equal 3, comparison happens. When I equal 4, also comparison happens. When I equal to 5, 5 less than or equal to 4, n equals 4, comparison happens but fails. So total how many times comparison operation is performed? 5 times, n plus 1. If you are counting this increment operation, how many times? 4 times. So that's why textbook, instead of writing n plus 1, they write usually n to avoid confusion. Okay? Is that okay? So how many times this operation is performed? For each value of I one time, I equals to 1 to n one time, this value is nothing but n minus 1 plus 1, that is n. If you are counting from 6 to 9, total how many times we counted? Not 3 times, no, 4 times. 9 minus 6 plus 1. That's what, okay? Now third step, what is the operation we are performing? Addition or assignment, both. Okay, no. So let us take addition operation. How many times addition operation is performed? For each value of I, one time. So sigma I equals to T3 of n is again same thing, we will get n. Fourth step, it is only written. So this is one time, T4 of n is 1. Then what is the total number of operations performed? 2n plus 2. T of n is total number of operations, that is 2n plus 2. Sir, second step, no? That we explicitly not mentioned. If we can multiply that with 2, but only one operation we counted. We counted it as one operation. Okay. Then total number of operations is 2n plus 2. If n is finite, 2n plus 2 is finite or not? Yes. Then we say that okay, Tn is 2n plus 2. It is not because there are 4 lines in the algorithm. Or Tn, if n is finite, Tn equals to 2n plus 2, that is also finite. Hence this algorithm has finiteness property. And this is called running time of this algorithm. It is not time, it is operation count. Is that okay? Okay. Now okay. Now in order to analyze, okay, directly I have written steps. So but we follow this procedure. First we need to decide on what is the parameter indicating input size. In this case we are given n elements, no? Array contains n elements. Input size parameter we can take it as n. Okay. Now next step is, what is the most important operation in this algorithm? What is most important operation in this entire algorithm? Either comparison you can take or actual work is this, no? This is addition operation. In this entire algorithm, addition is the most important operation. Then instead of counting for entire thing, you can count only how many additions are performed. How many additions are performed in this case? Only n. Then I will tell you why we are counting only that. Next one is, determine whether the number of additions performed, it only depends on n or actual values in the input also. That is instance of the problem. See, n is input size, T of n is total number of operations performed in our algorithm. Okay. Now T of n value, if I tell you n equals 4, will you be able to tell me exactly what is T of n? In this case, is it possible? How many additions are performed? We can tell no easily 4. N equals 5 means 5. But always it is not possible. That we will see one more example later after some time. Okay. Then you count T of n. After counting T of n, we will get summation expression. You simplify that. Then T to n. Okay. You will get T of n equal to n only. In this case, only additions we are counting. Then it is n. Here we are counting all operations. Here we are counting only additions. The difference, is it clear? Why additions, that I will tell you. Okay. Next one is, we need to determine what is the order of growth of T of n. This we will discuss now. Okay, this last part. Okay. In order to analyze algorithm, first we need to decide on parameter indicating input size. Next, what is the most important operation in that algorithm we need to consider. Next, most importantly, whether number of times that basic operation, most important operation in the algorithm is repeated for given input size. It depends only on input size or actual instance also. Okay. After that, we will get, if it is a non-recursive algorithm, we will get a summation expression. If it is a recursive algorithm, we will get a reconciliation. Then by simplifying that, or here in this case by solving that, we will get value of T of n. After that, we need to find order of growth. What is that? That we will discuss now. Now, before that, what does complex analysis of algorithm mean? What does analysis of algorithm mean? That is predicting the resources the algorithm requires. Okay, no, you are given an algorithm, how much time this algorithm is going to take when you go for implementation. The corresponding program is going to take, how much space it is going to take. These are the resources the algorithm requires. That is called analysis of algorithm. Then how much time that our algorithm is taking or how much space it is taking, that values we need to calculate, and respectively that we call it as this is running time complexity of this algorithm, this is called space complexity of the algorithm. Okay. Now, to solve a problem, we have two different algorithms. This is algorithm 1, this is algorithm 2. Both are solving the same problem, not different problems. Okay. Now, you tell me out of these two algorithms, which algorithm is better or efficient, or which is taking less time to solve the problem? First one or second one? Okay, there are both answers are there, no, but only one should be the answer, that we will discuss. So n equal to 1, 2, 3, 4. Here in this case, number of operations performed is more than number of operations performed here. Based on this, can you conclude that algorithm 2 is much better or taking less time than algorithm 1? That is not correct. So if I ask you a question, whether Subba Reddy can run faster or head of the department CSC NIT Warangal, whether madam's car can go faster, what is your answer? All of you give the same answer, no? Definitely HOD's car only goes faster than Subba Reddy can run. But okay, here you did not ask me how much distance you are going. All of you gave same answer, no? Here also, that means you kept more distance in mind. It is not 10 meters or 20 meters. 10 meters, 20 meters before they start gear and all change gear, Subba Reddy will reach. It does not mean that, okay. So here also same thing we need to do. Large values of input we need to take how many operations are performed in both algorithms. For example, n equal to 10. How many operations are performed here? 345, here 1025. If you increase, then this value is very much high when compared with this. That means for large values of input size only, how many operations are performed in each of the algorithms we need to calculate. Okay. If n is very large, 3n squared plus 4n plus 5. In that, if I remove 5, whether it matters much? If n is 3n squared, T of n is 3n squared plus 4n plus 5. T of n is 3n squared plus 4n plus 5. Now I assume that n is very large, as n tends to infinite. Can you say that T of n is approximately equal to 3n squared plus 4n? Approximately equal. Can you say that it is if n is very large, 3n squared? If n is very large in terms of very big value, whether we multiply with 3 or not, it doesn't matter, no. For large values, not for small values of n, for very large values of n. Can you see? So what is that we have done? We dropped all lower order terms. This is lower order term, this is also lower order term. As well as constant coefficients of highest order term. This is highest order term. In this is constant coefficient. This also we discarded. Whatever remains, that is called order of growth or rate of growth. So what is order of growth of this algorithm 1? N square. Algorithm 2? N square and 2 power n, which is more? 2 power n is very large value, no, that is exponential, this is polynomial. 2 power n is very large when compared with this. Okay. Then in order to understand which algorithm is better, you find out order of growth or rate of growth of running time of all the algorithms. Whichever has a lower order of growth, we conclude that that algorithm is better to solve the given problem. Is that okay? Okay. Now what is our conclusion here? Algorithm 1 is better than algorithm 2. Now what is order of growth here? N square. Order of growth here? 2 power n. Both algorithm A and algorithm B, they are solving the same problem. Which is better? Obviously algorithm A is very much faster than algorithm B, no, for large. Is that okay? Okay. So finally, whichever algorithm has lower order of growth, that is better to solve the given problem. And this way of analyzing, here we are estimating time, how much time our algorithm is taking for large values of n, as n tends to infinity. This type of analysis is called asymptotic analysis. We are doing for large values of input, not small values of, as n tends to infinite. Okay. What does analysis mean? predicting or estimating the resources our algorithm requires. Most of the time we talk about time. Why? Because time is more precious than, resource than memory. Okay. Now you tell me what is, can someone tell me what is order of growth of this T of n? N cube. What is order of growth of this? N square. What is order of growth of 20? Always order of growth is in terms of input size. Input size is n, so into n power 0. And these are basically used orders of growth. To solve a problem, one student has given algorithm whose order of growth is log n. Another student has given algorithm whose order of growth is n square. Which is better? Which is efficient? Log n is more efficient than n square, no. Okay. Now that's what we calculate. So now again we ask the question. If you are calculating running time for all steps, okay, no, each step, what is the operation performed, and then take summation over all steps, then drop lower order terms as well as constant coefficients of highest order term. Here we are calculating for each step. After that, what is that we are doing? We got this value, again dropping lower order terms as well as constant coefficients of highest order term. Then finally what remains? N square, no, in this example. If that is the case, why to calculate for all steps? You can concentrate on only those steps where most of the operations are performed. It gives order of number of additions. Number of additions. Input size is n, most important operation is addition. T of n, number of additions performed when n is input size, T of n equals to n. Okay. What is the order of growth of n? It is n only. Now, is it clear? Order of growth is n. Okay. So if when in this case asymptotic analysis, we are doing for large values of input size, so that what matters? Exact operation count doesn't matter. What is its order of growth? It matters. Okay. For this we have different notations. Okay. So these are commonly used notations: big O, big omega, theta, little o, and little omega. Let f of n and g of n be two functions, monotonically increasing functions. What does monotonically increasing mean? If n time taken from here to Hyderabad and time taken from here to Bhopal, which is more? Bhopal. Why? Because distance is more, time is more. Similarly here also same thing. So if n1 is n1 and n2 are input sizes, say if f of n1 is less than or equal to f of n2 and it holds for all n1 and n2, then we say that there is monotonically increasing function. Okay. And f of n and g of n are monotonically increasing functions. Now let S be a set 1, 3, 5, 7. The same set we can also write it this way, no? X such that x is odd and x less than or equal to 8 or less than 8. Both are same or not? Okay. Okay. Now I can say 3 belongs to S, 8 doesn't belongs to S. Both are correct, no? Okay. Similarly here, what is big O of G of n? Big O of G of n is also a set. It is also a set. What does it contains? It contains all functions in n, say f of n, such that order of growth of that function, whatever that set contains, is less than or equal to order of growth of g of n. Is less than or equal to order of growth of g of n. Okay, let us see with an example. Now, what is big O of n cube? G of n I have taken as n cube. What is big O of n cube? This is a set. It is a set. Then I need to say clearly what are the elements of this set. It contains all functions, say f of n, all are positive, okay, no, and monotonically increasing f of n, such that order of growth of OOG, order of growth of f of n is less than or equal to order of growth of g of n. Order of growth of f of n is less than or equal to order of growth of g of n. Is that okay? Okay. Now can you give any function whose value is, whose order of growth is less than or equal to n cube? At least you get some idea. Okay. Can you give any function whose order of growth is less than or equal to n cube? So big O of n cubed, we can write it as, can you write n cubed here? What is its order of growth? N cubed, less than or equal to condition is satisfied. Anything? 4n cubed plus 5n, is this correct? Here also order of growth is n cubed. Similarly 2.6. So like this we can write 2 right, but ensuring that their order of growth is less than or equal to n cube. Now is it finite set or infinite set? Infinite set, no, infinite set. Now can we say that n into n plus 1 by 2n squared plus log n belongs to big O of n cube. Is this true or false? What is its order of growth? N square. N square is part of this set or not? Yes. Why? Because it's less than or equal to n cube. Is that okay? No. If I say n power 4 belongs to big O of n power 3, no, that is wrong. Why? Because order of growth of n power 4 is more than n cube. Now if you see here, n square less than or equal to n square, n power 1.5 less than or equal to n square, 5 n power 0 less than or equal to n square. Is that okay? Now can you tell me what is the order of growth of this belongs to? Okay. Is it true? First one is true or false? True. Why? Because its order of growth is n cube. N cubed is less than or equal to n cube. Second one. True. N cubed is less than or equal to n power. Order of growth of this entire thing is less than or equal to order of growth of this. Correct? No. N cubed and n power 4. Correct only. Third one. False. N cubed, that entire thing, n cubed is less than or equal to n squared type. Order of growth comparison. This is not correct. Okay. Third one is false. Okay. Now this is very good book for algorithms. Most of all of us know. Okay, if you wanted to buy this textbook and you asked one of your seniors what is the cost of the book, that senior said it is very good book, cost is not more than 1 crore. Okay, then that is correct answer only, but happened to be your senior, otherwise your response would have been different. No. Okay. Then okay. Next you asked one more senior. That senior said that cost of the book is not more than 1 lakh. Okay. Okay. Yeah, now you got clarity that if you have 1 lakh, you can buy this textbook. Okay. You asked one more senior. That person said it is not more than 10,000. One more senior like this. No senior is lying to you. All are giving whatever information they know. It is like after you write an exam, competitive exam for 100 marks. If your parents come and ask how much you are expecting immediately after the exam, you say not more than 100. Then that response you can imagine. No. Okay. Now you tell me what are this? They are giving upper bounds on cost of the book. No. Among this, if all are true, which is your favorite bound? 1650. Upper bound, if it is as small as possible, then it becomes our favorite. No. Okay. Similarly, now let us check this. T of n is 5n cube this. What is its order of growth? N cube. It is n cube. Now can we say that T of n is big O of n power 1 crore? Yes. N cube is less than or equal to n power 1 crore. Order of growth. What about second one? True. Ninth up to 9th, all are true. But among that, which is your favorite? If T of n is not shown to you, this 5n cube, this entire function value is not given to you. Only T of n you are representing using this 9. This value is not shown to you. Then which is your favorite? 9th one is our favorite. No. Why? Because it is close to actual order of growth of the function. No. Okay. If there is 10th one like this, 10th one becomes our favorite. Among all are giving what type of bounds? Upper bound. Upper bound, whichever is smallest or lowest, that becomes our favorite. In this case, it becomes our favorite. If there is one more answer like T of n is big O of n cube, that becomes our better answer. No. Is that okay? Now you tell me big O notation gives what type of bound? Upper bound. If upper bound is smaller, then it becomes our favorite. Okay, it gives more actual information about the actual order of growth of that function. Okay. Similarly, little omega notation, big omega notation. What is big omega of g of n? It is also a function. it is a set. What does it contain? What does it contain? Similar to big O, it contains, I repeat, what is big O, you remember, no? Big O of G of n is a set. It contains all functions, say f of n, such that order of growth of f of n is less than or equal to order of n. That set contains n square, n log n, 2n square, 3n square, n into n plus 1 by 2, like that, all functions. Now, what is big omega of G of n? It is also set, similar to big O of G of n. But the only difference is, it contains all functions whose order of growth is. Is that okay? Okay, let us see. What is big omega of n cube? This is a set. Can you give me an element of this set? First of all, we can write easily n cube, no? N cube, n power 4, 2 power n. We know that 2 power n is more than n cube, no? Similarly, 4 into n cube plus 5n minus 6. So like this, whatever we want, we can write by ensuring that order of growth here is greater than or equal to order of growth here. Is that okay? Okay. Okay or any? Okay. Now if I say that n square is big omega of n cube, is it true or false? N square is big omega, this is false. N power 4 is big omega of n cube, this is true. Is that okay? Yes. Now if you see here, all are greater than or equal to n square, no order of growth. If you asked one of your seen that a person said it is not more than 1 rupee. 1 rupee or even not less than 1 rupee. 1 rupee or even more than 1 rupee. Another person said 10 or more than 10. All are correct answers. Out of this, which is your favorite answer? Last one. It is close to actual cost of the book, no. Provided no one is lying to you among that 8. Okay. Now similarly, if T of n is given, can we say that T of n is big omega of n power 0? Order of growth of T of n is n cube. So T of n is big omega of n power 0. Is this correct or not? N cubed is greater than or equal to n power 0. Correct. Here what is this? N cubed is greater than or equal to log n. This is also correct. N cubed is greater than or equal to n. This is also correct. Like that, if you compare, all are correct. Among this, which is your favorite answer? 9th one is our favorite answer. No. If there is one more answer like T of n is big omega of n cube, that becomes our favorite. Okay. It does not mean that first 8 are wrong. They are also correct, but that is our favorite. Okay. If okay, this is in this case, this becomes n cubed is there, means that becomes our favorite answer. Now theta means theta of G of n, again it is also set. Here it is same order of growth. That is the only difference. Little o means strictly lower order of growth. Little omega means strictly higher order of growth. Okay, let me. If you know the if you have understood the definition of order of growth, other things are automatic. So one side order of growth of f of n, the other side order of growth of G of n. In this case, 1, 2, 3, 4, 5. This we write it as 1 means f of n is big O of G of n. Second one is big omega. Third one is theta. Fourth one is little o. Fifth one is little omega. Is that okay? Is that okay? Okay. If you see here, theta of n square means whatever we have written here, all have same order of growth as n square. N into n plus 1 by 2 means if you simplify, its order of growth is n square. This is also n square. This is also n comes down, 4 goes up, log 4 base 2 is n square. Okay, all are n square. Here all are strictly less than n square, if you see whatever we have written here. Okay. In this case, all are strictly greater than n square, orders of growth. Is that okay? Okay, let us see the example. Okay, here this function order of growth is n cube. The first one, is it true or not? True. N cubed is less than or equal to n cube. So it is true. Is that okay? N cubed is less than or equal to n cubed, order of growth. Here second one, n cubed is less than or equal to n power 4. Only order of growth comparison, not okay. In this case it is n cubed is less than or equal to n square. False. Third one is false. Fourth one, true. N cubed is greater than or equal to n cube. Correct. Fifth one, true. Order of growth is n cube. N cubed is greater than or equal to n. It is correct. Fifth one is true. Sixth one, true. N cubed is greater than or equal to n square. Seventh one, false. N cubed is same as n power 4. That's what they are claiming. That is false, no? Eighth one, true. N cubed is order of growth. Here also order of growth is n cube. Both are same. It is true. What about ninth one? False. N cubed is strictly lower than n cube. That is wrong. 10th one, true. 11th one, false. Both equal is not allowed. 12th one, true. Is that okay now? 5 notation. It is like this if you compare, no. Analogous to this 5 notations here. Okay. Now, next one is, so given algorithm complexity and problem complexity, both are same or different? Okay, let me ask you a question. Is it possible to solve sorting problem in less than n time? Is it possible, is there any sorting algorithm which sorts an array of n elements in less than n time, or whose order of growth is less than n? It is impossible. No such algorithms are there. There are algorithms with restrictions which take n time, but definitely there are none with less than n time. Okay. So any problem, no, there is some internal difficulty of the problem. It is impossible to solve that in less than that much time. That problem definition itself, it tells us. Okay, no. So for example, sorting problem, is it possible to solve it in less than n time without restrictions on input? No. All elements are equal, we can sort it in no time without doing anything. That itself is, but without any restrictions on input. So sorting problem, it requires at least n time. That means any algorithm to solve sorting problem, running time, can you say that big omega of n? Running time of any sorting algorithm, it is big omega of n. Is that correct? N or more than n. Yes. Similarly, running time of any searching algorithm, can you say that it is also big omega of n without any restrictions on input? Don't say again array is in sorted order, binary search, not like that. Without any restrictions on input. Is that okay? Yes. What about square matrix multiplication problem? Is it possible to solve it in less than n squared time or not? It is impossible. Okay, no. Two square matrices of order n, there is no algorithm which solves them in, which multiplies them in less than n squared time. That is the internal difficulty of the problem itself. No, okay, no. Even if we give 100 years also, it is impossible to come up with less than n squared time algorithm. Okay, no. This is square matrix multiplication problem. Okay, no. You know that. So this is an algorithm. What is the running time of this algorithm? N square. Or what is running time of this algorithm? N cube. See, this 3 for loops. No, this for loop runs for n times. This is n times. This is n times. N into n into n, n cube times. No. Running time of this algorithm is n cube. But what is the complexity? We know that minimum it requires n squared time. Okay. No. So minimum is n square. But this algorithm takes n cube time. Minimum is n square. This whatever algorithm we have, so traditional algorithm, traditional way of multiplying, classical way of multiplying two matrices, it takes n cube time. N cube time. Now our goal is to reduce this gap. To reduce this gap. Some people do research in this direction. That means they come up with better algorithms so that the gap gets reduced. Some people do research in this direction. They say that this bounds they try to improve. For example, sorting problem, minimum is n time, but there is another result which says that is lower bound, which says that if it is a comparison based sorting algorithm, any sorting algorithm takes minimum n log n time. Bubble sort or insertion sort, selection sort, in the worst case minimum they take n log n time. Merge sort, heap sort, all are comparison based sorting algorithm. They compare one element with other element and rearrange the elements. But not bucket sort, radix sort, they are not comparison based sorting algorithms. So any sorting algorithm, it takes minimum n time. Later it has been some other result also there that shows that if our sorting algorithm is comparison type sorting algorithm, minimum they take n log n time. That means they are reducing the gap. No, here but here we know only this n square without restrictions on input. But later people have come up with different algorithms. Now this is in Volcker stress, and this algorithm majority of you must be knowing. It was in the year 1969. They published a result. It says that this is the title of their research paper, and it runs in n power log 7 base 2. That is approximately n power 2.81. It is better than n cube 2.81. The gap is reduced. No? Later, Coppersmith and Vinograd, they proposed an algorithm which runs in less than n power 2.81, n power 2.81, this algorithm. This is the way people do research. Later, in 2010, this is PhD thesis, they proposed an algorithm which runs in n power 2.374, which is better than previous algorithm. Their order of growth is less than or equal this. Later, she proposed an algorithm 2012, which runs in n power, earlier it was 374. She reduced how much? She lost from third digit onwards, that value has become less. Is that okay? This is better than previous algorithm. This is the way people do research now, coming up with a better algorithm. Later she broke her own record in 2021. This is top conference in theoretical, you can say it as one of the top good conferences. She proposed an algorithm and it runs in n power 3.7285. Earlier it was 8685. Okay, no. Now these are the list of algorithm. Okay, no. Matrix multiplication, minimum is n square time, traditional algorithm n cube, and this is this. Okay. Now is it clear what is, so square matrix addition, is it minimum it takes n square time, okay, without any restrictions on input. Matrix multiplication, minimum n square time. Big omega means that it gives lower bound. Now we know that now. Okay. Sorting problem, minimum n time. If it is a comparison based sorting algorithm, minimum n log n, big omega of n log n. Okay, like that. So finding sum of elements in the array, minimum n time you require, no, without restrictions on input. All elements are same means that is different. Okay. So minimum spanning tree problem, graph should be given number of vertices and number of edges. Minimum is number of vertices time, no. Okay. So these are called complexity minimum. Okay, no, problem complexity. Okay. Now, if there exists a polynomial, the worst case running time of an algorithm, if you can represent it as big O of n power c for some constant c, where n is input size, then we say that that problem is a that algorithm is a polynomial time algorithm. What is worst case running time of bubble sort? N squared. Is it of the form big O of n power some constant? Yes. What is worst case running time of binary search? Log n. Log n. Is it of the form big O of log n? Can we write it as big O of n? Log n equals to big O of n. Is it right or wrong? Log n's order of growth is less than or equal to n's order of growth. No. It is also true. That means binary search is also a polynomial time algorithm. No. Okay. So to solve a problem, if there is at least one polynomial time algorithm, then we say that that problem is in complexity class P. Okay, no? That problem is in complexity class. Can you give an problem which is in complexity class P? You might have learned many algorithms. Sorting problem, is it in complexity class P? There are so many algorithms, no, merge sort, quick sort, bubble sort, they run in n square time or n log n time. That is polynomial only, big O of n square we can write. Matrix multiplication also, already we have seen n cube time algorithm or n power 2.71 or Coppersmith-Vinograd algorithm. Okay. Sorting problems, all are in complexity class P. Okay. Now finally, we try to understand what is worst case running time, difference between best case, worst case and average case. Maybe I will not explain average case. Okay. searching problem. Okay, no. What is input? Sequence of n elements and another element called key. Output is, we can say yes or no, or position of that element, something like that. Now these are different instances, no? So in this instance, if key is 20, how many comparisons we perform if I use linear search? 1. In this case, key is 15. How many comparisons? 3. In this case, 5. In this case, 7, no? 7. Here, if instead of 35, if this value 500, 800, 90, 1000, 450, 600, 35, still it is 7? Okay. Now can you tell me, in this algorithm, this is linear search algorithm, what is input size here? Number of elements given to us, that is n. Okay. What is most important step in this algorithm? Most important operation in this algorithm? Comparing. Our goal is to find whether key is present in our array or not. Every element, first element of the array, we compare in linear search. It happens that way. No, first element we compare with key, not equal means second element you compare with key, not equal. Third element you compare with key. Keep doing like that. Here, what is the most important operation in this? Comparison. No, a of I not equal to key. This comparison is our most important operation. Let t of n be the number of times comparison operation is performed. T of n be the number of times comparison operation is performed. Okay. Okay. Now, this is the procedure we follow to find running time of algorithm. Okay. N is input size. Most important operation is comparison. Now you read this. Check whether the number of times basic operation is executed depends only on the input size. If I say there are 4 elements in our array, okay, input size is 4. Can you directly tell me how many comparisons are performed in that case? It depends on the position of key. Even if I tell you what is input size, it depends on actual values in the input. That's why even if I tell you input size, you are not able to say exactly how many times that basic operation is performed. Then in that case, what is that we do? We say that it not only depends on n, but also actual values in the input. That is an instance. In that case, what is that we do? What is the given input size n? What is the minimum number of times that operation is performed? What is the maximum number of times that operation is performed? On average, what is the number of times that operation is performed? We calculate. Respectively, we call them as minimum number of times means best case, maximum number of times that is performed is worst case, the other one is average case. Okay. In this case, see, same input size, but different inputs, answer is changing, no, as you said. Okay. In this case, we go for different cases, best case, worst case, average case. Okay. Now let us see what is best in the best case. What is the best case running time of linear search? When does best case occur? Okay. First element is in key is in first position. Best case occurs. Okay. In that case, what is T of n? T of n equals to 1. What is its order of growth? N power 0. Okay, no? Order of growth is n power 0. In the best case, its order of growth is n power 0. T of n is 1. This one we write it as n power 0. That means order of growth is n power 0. When does worst case occur? Element is present in last position or not even present in the given array at all. In that case, how many comparisons we perform? N. What is the order of growth? N only, no? In the best case, order of growth is n power 0, that is 1. In the worst case, order of growth is n. Average case, it is between best case and worst case. We know that that is also n. Okay, no? I am not doing that. So always, this is the relation. No? We know that best case running time is less than or equal to average case, less than or equal to worst case running time. Now let me say, worst case running time of linear search is big O of n. Is that true or false? What in the worst case, what is order of growth? N. N is big O of n. That's what they are saying. Is it true or false? True. First one is true. What about second one? Worst case running time of linear search is big omega of n. What is in the worst case? What is its order of growth? What is its order of growth in the worst case? N. So that means it is n is big omega of n. That's what they are asking. No, n is big omega of n. n is that true or false? See, n is big omega of n. Is this true or false? Only asymptotic notations, that's all. Only. What is big omega? This side order of growth should be greater than or equal this side, no? It is greater, equal only, no? So that means it is true. What about third one? Worst case running time of linear search is theta of n. True. Now if I say running time, worst case running time of linear search is big O of n power 100. Is this true or false? Why false? In the worst case, what is its order of growth? N. N is big O of n power 100. N is less than or equal to n power 100 only, no? Technically it is correct, but no textbook writes that way, no? Because upper bound as simple, as small as possible, then it gives more information about actual running time, no? It is not wrong answer. It is like after writing exam, for 100 marks, how many you get means not more than 100. Is it correct answer? Correct only, but useless answer, no? That means not useful. Is that okay? Like that only, okay? It is correct only, but not useful, okay? Now what about this? Okay, let us talk about sixth one. Running time of linear search is theta of n. Is that true or false? See, here I am explicitly it is worst case running time. Here it is simply running time. Running time means it should be true for best case also, worst case also, average case also, no? So running time of linear search. In this case we need to check best case it should be true, worst case it should be true, both cases it is true means automatically average case it is going to be true, no? You check for two cases. Best case, is it true? No, no. In the best case it is n power 0. N power 0 is theta of n. That is wrong, no. That means sixth one is false. What about fifth one? This is also false. It should be true for best case, worst case and average case, three cases. But why? Because here explicitly it is not given, no, whether best case or worst case. So it is n power n. In the best case it is n power 0. N power 0 is big omega of n. That is wrong, no. Worst case it is true, but in the best case it is not true. Hence that statement is true or false? Fifth one is true or false? False. What about fourth one? True. Best case it is n power 0, big O of n, correct. Worst case it is n, big O of n, correct. That's why you might have read, okay, worst case running time usually big O notation is preferred. Why? Because if you represent worst case running time using big O notation, it is true for worst case, best case also, average cases also. That's why big O notation is preferred. That is the only. Is that clear? But always which is our favorite notation? Theta. You are telling no. What is the cost of the book means 1650 over. Less than or equal 16, that is again confusion, no, whether it is 1650 or less, or greater than or equal 1650 means again it can go up to 1000, okay. So finally, is it clear? Only fourth one is true. First to four statements are true here. Fifth and sixth is wrong. Is that okay? Okay, now you tell me, okay. In the best case, what is order of growth? N power 0. N power 0 is big O of 1. Is this correct? Yes. You forget about what is the algorithm given to you. Simply its order of growth, you know. Asymptotic notation definitions, if they are clear, automatically you should be able to answer. N power 0 is big O of 1. Is that true or false? 1 means n power 0. N power 0 is less than or equal to n power. That is true. What about second one? True. Third one? N power 0 is theta of n power 0. True. First three are true. Now let us check fourth one. Is it true? Here best case is not given. It is in general. All cases of by this linear search, it should be true. Best case it is true, but worst case it fails. Hence this statement, fourth statement, is it true or false? False. What about sixth one? False. Best case okay, but worst case also it should satisfy, no. Sixth is false. Fifth one, true. That's why you say, usually we read in textbooks, no, best case running time, big omega notation is preferred. Why? Because if you represent best case running time using big omega, it is true for other two cases also. If you remove best case and read, still it is correct, no? That is the reason big omega is preferred, okay? Now you tell me, first one is true or false? Okay, last 2 minutes, close. The first one is true or false. Best case running time of linear search is big O of 1. What is best case? N power 0. N power 0 is big O of 1. True or false? True. What about second one? Best case running time of linear search, we know that it is n power 0 order of growth. N power 0 is big O of log n. True or false? True. What about third one? N power 0 is big O of n. Why? N power 0 is big O of n. That is correct only, no? Okay. What about fourth one? True. Up to 11th, are there any wrong answers? Yes, okay. What about 12th one? Best case running time of linear search is big omega of log n. False. N power 0 is not greater than or equal to log n, no. 13th one? False. 14th one? False. The reason, is it clear why? N power 0 is n, that is wrong. Here n power 0 is greater than or equal to n, that is also wrong. Red color, they are wrong statements. Okay. Similarly, worst case. First one, is it, oh, already the algorithm is clear, no? You can, okay. Worst case running time of linear search is big O of 1. Is this true or false? Why? It is n. N is big omega of 1, that is wrong, no? Here it is n. N is big omega n power 0.2, that is wrong. All other things are correct. Anyhow, it is said with you, we can. Definitions of 5 asymptotic notations clear? So what is order of growth? Okay, what is order of growth? In this given a function, remove all lower order terms as well as constant coefficients of highest order term, only constant. Again, after getting 7n square, after removing 7, again don't write that n into n, I will remove n. Then this n 1 into n, I will remove this n, everything will get 1, not that, only constant coefficient, no. Okay. What is its order of growth? N square. Drop lower order terms as well as constant coefficients of highest order term, whatever remains, that is called order of growth or rate of growth of running time of that algorithm. Here it is similarly 2 power n. To solve a problem, if you have multiple algorithms, whichever algorithm has lower order of growth, the corresponding algorithm is better to solve that problem. If this is the case, we are interested in order of growth, then why should we calculate for each step in the algorithm what is the operation performed and how many times it is performed, again take summation, again discard. Instead of that, you only can cleverly choose what is the most important operation performed in that algorithm, you count only that operation. All sorting problems, what is the operation we count? Comparison. All searching problems, searching means, I am talking about linear search, binary search, these algorithms. What is that we count? Comparison only. Okay, that is most important operation. Okay. Now, these are commonly used orders of growth. This is lowest and this is highest among this. Now, this way of analyzing algorithm, this we call it asymptotic analysis. For that, we have different notations: big O, big omega, theta, little o, little omega. What is big O of g of n? It is a set. It contains all functions whose order of growth is less than or equal to order of growth of the given function. Big O of n square contains all functions whose order of growth, positive functions whose order of growth is less than or equal to n square. Is that okay? Once one big O is clear, means other things only notation change, that's all. Big O notation gives what type of bound? Upper bound. Upper bound high is our favorite, or as low as smaller value is our favorite? Low. Why? Because you can observe from this. Because running time of linear search, I can say T of n is n power, big O of n power 1 crore also. Big O of n also. Both are correct. Which is our favorite? Big O of n. Okay. Similarly, big omega gives lower bound. It is as high as possible, that becomes our favorite. Otherwise, simply if they give some algorithm, what is the running time? Simply you can put big omega of 1 now. After writing any exam, you can say I will get 0 or more than 0 marks. Correct only, no, always. Okay. But this is not useful. Okay. And the difference between problem complexity and algorithm complexity. What is polynomial time algorithm? With the worst case running time of an algorithm, if you can represent as big O of n power c, where c is a constant and n is input size, then we say that it is a polynomial time algorithm. And if there exists at least one polynomial time algorithm to solve a problem, then we say that that problem is easily solvable or efficiently solvable, and it is said to be in complexity class P. Is that okay? These are examples for problems in complexity class P. If you are not able to exactly say what is the number of times a particular operation is repeated in the given algorithm, then we calculate best case, worst case, and average case. And respectively, we can calculate running times. And best case, which notation is preferred? Big omega. Why? Because if you represent best case running time using big omega, it is true for other cases also. Similarly, worst case, which is better? Big O. Why? Because it is true for other cases also. Okay, thank you. Thank you. Thank you. Okay. Now we'll have break for some 10-15 minutes. 10:55 again we assemble here. Okay.
So that's good. We will, use it to understand the algorithms, even the quantum algorithms, going ahead. Okay. All right. Great. So now, okay. So yesterday we saw Deutsch's algorithm, right? Deutsch's algorithm, and we saw how we are getting an advantage in the quantum case. It was a simple problem, but we saw a query advantage. Again, a small advantage, 2 versus 1, right? 2 classical queries versus 1 quantum query. Now we'll see a larger advantage, okay? A much larger advantage. So, right here. Okay, so the task for the Deutsch algorithm is similar. It's a generalization of the task for Deutsch's algorithm. The task is what? We are given a function f. Now, from 0, 1 to the small n to 0, 1. That means if you, let's call capital N as 2 to the small n. Capital N is 2 to the small n. You have capital N bits in the database. Capital N, that is 2 to the small n bits in the database. These are all bits 0, 1, 0, 1, 0, 1. What is promised to us? The promise is either all of them are zeros or all of them are ones, or exactly half are zeros, exactly half are ones. Okay? Exactly half are zeros, and where the zeros are, where the ones are, is not clear. Can be anywhere. But this is the promise. Either all of them are zeros, all of them are ones. That is called as the constant function. Everywhere it is 0, everywhere it is 1. Balanced function is exactly half are zeros, exactly half are ones. That is balanced. We have to determine which is the case, whether it's a constant function or it's a balanced function. But we don't know the locations at, if it is for example a balanced function, we don't know where it could be zeros, where it could be ones. Now, suppose we want to come up with a classical algorithm for this. What will we do? We have to go and query the bits of the database. Agreed? Worst case, how many queries? Suppose small n is 6. 2 to the 6 is 64. So there are 64 bits in the database. You want to determine whether it's a constant function or balanced function. What will you do? Check one by one. If you check one by one, how many bits you have to check? 64, or you can do with less. How can you do with less? Pardon me, 32, yes. Exactly. If you look at 33, start from left, 33 you check. If everything is 0, then it has to be a constant function. It is not balanced. Remember, balance what we said, 64 meaning exactly 32 are zeros, 32 are ones. But if 33 are turning out to be zeros, it cannot be a balanced function. And some of them are turning out to be 0, some of them are turning out to be 1, it has to be balanced. It cannot be constant function. So if you look at 33, that's enough. So just one more than half is enough. Okay. But the point is, you cannot do with lesser than that. Because suppose you start to look, okay, then maybe all are turning out to be zeros or all are turning out to be ones. So you cannot still be sure. You have to look at 33. Now, this is if you have a classical deterministic algorithm. That is, you want to give the answer with probability 1. However, if you want to give the answer with probability, I want to answer with probability 0.9. It's enough. So I use a randomized algorithm. Okay, randomized algorithm. Then how many queries are enough? Think about it this way. Okay. So in the morning, Professor Subbareddy covered some type of algorithms. He mentioned some type. Did he also mention randomized algorithms? Huh? No. Randomized algorithms are like this. Suppose you toss some coins. Okay. Toss some coins, and as you toss coins, you look at some entries of the database randomly. Okay. So out of the 64 locations, I am randomly looking at this location, that location, this location, like that I am looking. Not deterministic, randomly I am looking. Then what is possible? You see what I am saying? So if I randomly look at 10 locations, if it is all zeros, what will happen? All the 10 locations will turn out to be zeros. If it is all ones, and if I randomly look at 10 locations, what will they turn out to be? Ones. If there are half zeros, half ones, if I randomly look at 10 locations, approximately how many will be zeros? How many will be ones? 5, 5. Maybe it can be 6, 4, like that. 7, 3 even, possible. But it will be around 5. It is very unlikely that you look at randomly 10 locations, all of them turn out to be zeros. What is the chance? There are half zeros, half ones. You are randomly looking at the locations. Each time you look at a location, the probability of seeing a 0 or a 1 is half, right? Because they are half, right? Suppose instead of 64, I have like, 1000 bits, 10,000 bits in the database. Half are zeros, half are 1. I am randomly looking. What is the chance that if I look at 50 locations randomly, all of them turn out to be zeros? Very, very tiny, right? Extremely tiny. Agreed? It's like I am tossing a coin, okay? Balanced coin, head or tail. I toss 50 coins. Each of them turn out to be head. What is the chance? 2 to the minus 50. The probability that everything turns out to be head is 2 to the minus 50, right? Because first coin turns out to be head, probability half. Second coin turns out to be head, probability half, because these are unbiased coins, independent of each other. Third coin also head, half. So half into half into half into half into half, like that 50 times. That is 2 to the power 1 over 2 to the 50. Very tiny probability. So most likely we will see approximately half, 25, around 25 zeros, 25 ones. Maybe it will be like, I don't know, 22, 28, like that. But it won't be very, very skewed. You won't get like 5 zeros and 45 ones. Very, very low chance. So therefore, similarly, in this database, which has half zeros and half ones, if we are randomly looking, each time we look, we'll see a 0 with probability half, 1 with probability half. Then if we look at 10 times, 20 times, 30 times, 50 times, 100 times, we will definitely get a few zeros and a few ones with very, very high probability. So, randomized algorithm, if my probability, if I want to make the probability as small as epsilon of making error, okay, think about it this way. Suppose I want, as we talked before, right, for the coins, if you're doing coin tosses, if I do 50 coin tosses, the probability that I only see zeros, the probability is 2 to the minus 50. So probability of only seeing zeros is our error event, right? So if I want that error event to have a probability smaller than epsilon, I need number of coin tosses k, so that 2 to the minus k is epsilon. Agreed? Epsilon, think of epsilon as a tiny number. I want 2 to the minus k to be epsilon. Okay? This is my error event. I do k coin tosses, right? 2 to the minus k is epsilon. It implies what? K is like log 1 over epsilon. Agreed? Log 1 over epsilon. So I should toss k coins, which is log 1 over epsilon, to see at least 1, 0, 1 head. Okay? So therefore, same thing will happen in that database. Okay? If you have half zeros, half ones, if you look at k locations randomly, the probability that you will see either 1, 0 or 1, 1 at least is going to be 1 minus epsilon. Only with probability epsilon you will see all zeros or all ones, roughly. Okay? This is like we are just doing a broad argument here. So if I want to make the probability of, okay, so what will happen? I have all these bits in the database, okay? I randomly look at k locations. If all of them turn out to be 0, we say it's a constant function. If all of them turn out to be 1, we say it's a constant function. We see either a 0 or a 1, we say it's a balanced function. Okay? Now what is the probability that if it is a balanced function and we say it is a constant function? Is that a chance? Okay, firstly, if it is a constant function, is there a chance that we will say it is a balanced function? Never, right? Because constant function, even if k we look, will all be turned out to be the same. So we will never err in that direction, that if it's a constant function, we'll always say it's a constant function. But if it's a balanced function, what is the chance that we will say it is a constant function? Because we're looking at k locations, all of them turn out to be zeros. What is the probability? 2 to the power minus k. All of them turn out to be ones, again 2 to the minus k. So let's say 2 times 2 to the power minus k. But that's a tiny probability, right? I want to make that probability suppose smaller than 0.01. How much I need? Log of 1 over 100. Sorry, log of 100. Log of 100. Log of 100 is how much? 7, 8, whatever. I don't know how much it is. 2 to the power 7. 2 to the power 7 is already 128, right? So let us say I randomly look at 10 locations. I can be very confident my error will be smaller than 1 over 100. Agreed? I look at 10 locations. If I look at 20 locations, I am even more confident. So 20 locations, but that is independent of how many are actually there in the database. You see this? Small n could be 1,000 or 10,000, a million, 1 million, doesn't matter how long it is. If I just randomly look at 20 locations, I am very confident of my answer. Correct? If I want to ensure that my error is smaller than 1 over 100, it is enough for me to look at 20 locations. Correct? It doesn't matter how many actual bits are there in the database. So the randomized algorithm, we will say, has a query complexity constant. For a constant error, suppose I have fixed my error to be some epsilon, which is constant, then my query complexity is a constant, scaling like log 1 over epsilon. It has nothing to do with n. See, he gave examples, right? Whenever we're talking about complexity, we count it in terms of n. What is the n? N is the number of bits in the database, either small n, big n, whatever. But the point is that here the time complexity has nothing to do with n. However, remember, for deterministic algorithm, time complexity had to do with n. It was 2 to the power small n divided by 2 plus 1, let us say. Correct? Deterministic algorithm. Deterministic algorithms scaled like for deterministic algorithm it was like 2 to the n over 2. Agreed? Randomized algorithms is like order log 1 over epsilon, right, for epsilon error. Now that's constant, nothing to do with n. Okay? Now you will see the quantum algorithm for this problem will be constant. In fact, one, like how it was in the yesterday, Deutsch, the task for that. So here is a task where deterministic algorithms take exponential number of queries, 2 to the n, exponential. Randomized algorithms constant, but still it is like log 1 over epsilon. Quantum algorithm 1. So quantum algorithm is doing exponentially better than classical deterministic algorithm, but not so much better than classical randomized algorithm. Later we will see a task where it will do much better than even classical randomized algorithm. Currently it is doing better than classical deterministic algorithm, not so much better than classical randomized algorithm. Later we will see a task where it is quantum algorithm will do better than classical randomized algorithms. Agreed? Quantum algorithm we don't say deterministic, although you can see usually quantum algorithms inherently have some probabilistic nature, right, because you are measuring and all that. But it is possible that you can still design quantum algorithms which give you the answer with probability 1, always correct, in which case you can call them in a sense deterministic because they are never wrong. At least as long as your gates are ideal and all that. As long as your gates are all ideal, you are analyzing it using ideal gates, then it is never wrong. That one you can call it in a sense deterministic. But otherwise quantum algorithms are inherently probabilistic because there is going to be superpositions involved and all of that. Okay. Any other questions? All right. So this is going to be our problem. Right. What is the okay? So we understood what the problem is, the task is, right? What the task is. Now let us look at what the circuit is. This is the circuit. Okay. It is very similar, if you know, to the Deutsch's circuit. Deutsch's circuit had basically, so here you have zeros, n zeros, n wires, small n wires which are zeros, and one wire coming as the 1. In Deutsch's case, n was 1. So there was a 1 wire coming with 0, 1 wire coming with 1. All of them has Hadamard gates here. Then this BF query followed by Hadamards on the top n wires. Last n wire we trash as before. Then we go ahead and measure all these n wires, and that is going to be, that will help us determine our answer. Okay? Good. So now what is the case? Okay? Oh, sorry. All right. Okay, so we will start analyzing it now. Okay? Start analyzing it. Now, you see, this BF as before, right? Let us recall what was BF. BF was for every input X on the top n wires. Remember, n wires have n bit input, and the last wire is 1 bit B. The action of BF is it takes X and B to X and B parity f of X. Note that X in this case is n bits, but f of X is still 1 bit. F of X is still 1 bit, X is n bits. So therefore, B is also 1 bit, X B go to X B parity f of X. This is how the value of f is obtained using BF. Okay? Good. That's our BF. Now, okay, this is one of the things we will see maybe in one of the tutorials. This is a good homework exercise also for you guys. Remember, we know what is the action of Hadamard on one single bit, one single wire, qubit. We know what is its action. If I have n Hadamard gates acting on n qubits on a n bit X, n Hadamard gates acting on n bit X, n wires, the action is 1 over square root 2 to the n summation over y 0 1 to the n minus 1 x dot y ket y. Okay? Ket x goes to this one here. What is x dot y? X dot y is, remember, x is n bits, y is n bits, so x dot y is summation I from 1 to n xi times yi summed over mod 2. We understand what is mod 2? Mod 2? Please raise hands who understand mod 2. Okay. Mod 2 simply means if you have a number 13, you go mod 2 means you divide by 2 and look at the remainder. Remainder is 1. If you look at 14, remainder is 0. 15, remainder is 1. That's mod 2. Divide by 2, look at the remainder. So what you are doing, if you have n bits in X, n bits in Y, you are simply multiplying each bit together, adding them up and going mod 2. That is called no. Yeah. So there's a bracket here. Actually, it is you sum it first, then you go mod 2. Okay. So therefore, the answer is either 0 or 1, because the remainder will only be 0 or 1. That is what you do, minus 1 to the that mod 2 and ket y. This is what is the result of doing n Hadamards on ket x. Agreed? Yes? Yes?
Sir, after summation of xi, yi, then we'll do mod 2. The
Yes.
result of xi and yi will do mod 2, right?
Xi, yi, you sum over all I.
After that, we'll do mod 2.
Yes. Xi, yi is simply the product. Bitwise product. Clear? Okay. So, this is the formula we are going to use for n Hadamard. We will try to cover this up over tutorial if possible. In any case, please try to do this as a homework exercise. Now, this one we have already seen before, okay? Ket A minus ket 1 parity A is minus 1 to the A, ket 0 minus ket 1. We saw yesterday. Okay, now let's analyze. Okay, remember what is happening here? First we are taking n zeros and doing Hadamards on the n wires, and the last wire there is a 1 and we do a Hadamard. So, if we use that formula, n Hadamards on the first n zeros followed by 1 Hadamard on the last 1. Agreed? So, if we use the formula, you see it is summation y minus 1 to the x dot y. X here is all zeros. So, x dot y is what? If you have all the xi's are zeros, so xi dot yi is 0. You sum it over 0. Go mod to 0. So, therefore, minus 1 to the x dot y is 0 for every y. But if x dot y is 0, minus 1 to the 0 is 1. So, there is a 1 here which we are not writing. So, it's summation over y ket y. Agreed? Yes? Okay. Then Hadamard on ket 1, that is usual, we know this one, ket 0 minus ket 1. Now, let us club all these constants here, and now we are doing BF. So, psi 2 is after we have done the BF. BF, what happens? Look at this, there is a y here and a 0 here. So, y f of y, that is 0 parity f of y. Then there is a y here, there is a 1 here, you get y and 1 parity f of y. The minus sign is here. Agreed? Yeah, you have a question? Yes, please. Repeat that one. Okay, I am just saying, remember what happened in our circuit? We did this n Hadamards, and so we got psi 1. Then we did BF, we got psi 2. So, we are trying to see what is psi 2 after application of BF. So, psi 1 we got already, which was this, okay, using the formula for n Hadamards. Then we are looking at what is psi 2. Remember what is the action of BF? It takes this thing, the n bit input, whatever it is, and this one, and does parity f of y. So, y and 0 becomes y and 0 parity f of y. 0 parity f of y is f of y. Then y and 1 becomes y and 1 parity f of y. That is 1 parity f of y. Then the minus is already there. That's all. Okay? Any questions? Okay. Now, now you take common out, y. Take common out. Your bracket f of y is here, 1 parity f of y is here with a minus sign. Okay, that is common. Good. Now what happens? Now you see, same formula, remember that formula we are using now. A minus 1 parity A is minus 1 to the A is 0 minus 1. this formula here gives us, think of this as A, f of y is A. A minus 1 parity A becomes minus 1 to the A, 0 minus 1. That one comes here, y is here. Now everywhere there is 0 minus 1, so we take it out, bracket here summation over y. Okay? Agreed? Okay. Remember, formula is ket A minus 1 parity, ket A is minus 1 to the A, 0 minus 1. So that's what we did. Think of this as A. A minus 1 parity A, because minus 1 to the A, 0 minus 1. That one comes out here. There is y here. There is the summation. Summation is here. This is always 0 minus 1 for every y. Agreed? So we take it out and we have it here. Okay? Agreed? Yeah. This is going inside the, if you take it inside the bracket, you will get 0 minus 1 with every y. Here? No, here we just taking the sum out, that's all. There is a summation over y, we take summation over y here. Yeah, like y with f of y and y with this, that is like a distribution over addition. Okay, so now eventually you see, as before we got f of y in the phase. Remember, b of f was always giving f of y in the last wire, correct? But now we got f of y in the sign, minus 1 to the f of y with y. This last wire is fixed at 0 minus 1. That is what we call as phase kickback. Phase kickback. Good. So we got psi 2. Fantastic. Phase kick, I mean, it's just a term we are saying. The point is this: b of f, when we use b of f, we always get the value of f. Like if I use b of f on y, I'll get f of y. But f of y I'll get on the last wire, right? B parity f of y. The value will come on the last wire. But by doing all this stuff, we are able to get the value of f of y as in the sign, minus 1 to the f of y. Here. Correct? We are able to get the value of f of y in the sign. That is what we call as phase kickback. Just a term to say. Okay. But the important thing is, to get this value of f of y in the sign is important. This helped us in Deutsch's algorithm. This is also going to help us in this algorithm. Getting the value of, so the first thing that they do is they get the value of y, f of y in the sign. Okay? This is the first thing they do. Okay. Now once that is done, now they are going to do okay. Psi 3. Psi 3 had what? It had again n Hadamard's on the first n wires. Okay? N Hadamard's on the first n wires. Last wire we are ignoring. So here in the analysis also we are just simply ignoring the last wire, which is just sitting at 0 minus 1 in tensor. So we are just ignoring it. Huh? Okay. So we did Hadamard and Hadamards on the first n wires. Again we use the formula. We get, here is summation over y that comes out. Now we get a summation over x minus 1 to the x dot y ket x. Agreed? Yes? Simply we use the formula. Good. Now you can see that we can exchange the summation. There is summation over y, summation over x. We exchange it. We take ket x here. Minus 1 to the f of y, minus 1 to the x dot y. Remember the formula? It goes to the parity, numerator, on the exponent. Minus 1 to the f of y, parity x dot y. Agreed? Yes? We got that. Now what we are going to do is, let us analyze, we are going to measure, remember we are going to measure the first n wires. So we are measuring this x. What is the probability that we get all zeros? X is all zeros. Remember, whenever we do that, the probability, if you have summation alpha x mod x, summation x alpha x ket x, the probability of getting x is mod alpha x square. Agreed? So this is your alpha x. It's a number, no? This is your alpha x. I mean divided by this 2 to the n is your alpha x. So mod of this thing square is going to be the probability. Agreed? Good. So we square this 1 over n, 2 to the, it comes 2 to the 2n. This thing is squared. But see, we are talking about x equal to all zeros. X equal to all zeros, what is x dot y? 0. X dot y is 0. So f of y parity 0 is f of y. F of y. Minus 1 to the f of y. So finally, after doing all this analysis, we arrived at the fact that once we measure, the probability of all zeros turns out to be this number. Correct? Agreed? Very good. Now once it is this number, let us look at it. If f of y is 0 everywhere, minus 1 to the f of y is what? 1 for all y's. Agreed? There are 2 to the small n y's, remember. For all of them it is 1. Sorry, f of y is 0, so minus of f is 1. So the summation is what? This summation is 2 power n. Correct, because for every y there are 2 to the power n y's, and for every y it is 1. So it is 2 to the power n. Then you square it, 2 to the power 2n. There is a factor here. Everything cancels out, you get 1. So that means if f of y is 0 everywhere, then this number is 1. If f of y is 1 everywhere, what is this number? F of y is 1. Minus 1 to the 1 is? Everywhere you sum, minus 2 to the n. Square it, 2 to the power 2n. Divide by 2 to the power 2n. Back to 1. That means if it's either everywhere zeros or everywhere ones, probability of getting all zeros is 1. Okay. And let us see if it is a balanced function, what happens. If f is balanced, half the places it is 1. What happens to this summation? What will be the summation here? Cancel out, because half the places it will be 1, half the places will be minus 1. Cancel out. See, this is the entire power of quantum is coming, you see, in the plus and the minus. This cancellation, this is what they call as constructive interference and destructive interference. The plus and the minus cancelling and all that. So, this cancels out, becomes 0. So, if f is balanced, it is 0. Agreed? So, our algorithm is, we perform that circuit, we go ahead and measure. If the answer is all zeros, we say f is constant function. If the answer turns out to be anything else other than all zeros, we say it is balanced function. Why it is correct? Because we know that if it was a constant function, we would have got 0 with probability 1. If it was a balanced function, we would have got 0 with probability 0. So, the all zeros is our indicator. If it is a constant function, we will always get all zeros. If it is a balanced function, we will never get all zeros. We can get other strings with different probabilities, but we will never get all zeros. So, what is our algorithm? When we get all zeros, we say it's a constant function. When we get any other string, we say it is a balance. Agreed? And now we are correct with probability 1. We are never erring. So, in that sense, it is a kind of a deterministic quantum algorithm, because we are never erring. Even this algorithm, randomized classical algorithm, is erring at least with probability epsilon, no? Here we are erring with probability 0. We are always correct. Agreed? Any questions? Yes, I agree. See, till now we are seeing some tasks which are giving us some kind of an advantage for the quantum algorithms. However, these tasks appear to be a bit artificial, right? This is for promise problem, right? Oh, we are promised that the database is either 0 or 1 or exactly half 0. Point is, when will this occur, right? So, at this point we are not looking at real world inspired problems or use cases inspired. We are simply first trying to determine, are there any problems for which we can exhibit some quantum advantage. Okay. Once we can exhibit that, then we will try to move towards more real world useful problems. Okay. So, the point is that people initially, this is Deutsch, the initial times. Initially, they came up with these kind of promise problems to exhibit quantum advantage. Then, next thing we will see is the Simon's algorithm. That may appear to be slightly more natural problem. Then will come the factoring. That is definitely a real world useful problem. So, but this was the pathway, you see. First came Deutsch, then came Simon's, and Simon's became an inspiration for sure. So, this was the pathway. Then there is a lot of work done on quantum algorithms, on group theoretic problems and so on. So, there are a lot of problems in the literature for which they have analyzed quantum algorithms. Accordingly, one can try to take inspiration from those tasks, that if you have a quantum algorithm for this task, maybe for a related task you can hope to get an algorithm. Things like that. But as such, there is no like a very easy way to say, oh, here is a class of problems for which we can get quantum speed up or not. It's not a very clean or easy way to say that. It is different things. I don't know whether you are aware of this concept of NP-hard problems. NP-hard problems, we don't expect a huge quantum advantage. I mean, we don't expect, for example, a polynomial time algorithm for NP-hard problems. It is possible that we may get it. It is possible. I mean, in fact, even it is possible that you may have a polynomial time algorithm for NP-hard problems. Possible. Because as such, we don't have any proved lower bounds. However, we don't expect. Similarly, we don't expect quantum polynomial time. So now you guys are aware, right? Polynomial time and all that from morning's lecture. So we don't expect polynomial time algorithms for NP-hard problems. NP problem, yes, but NP-hard, no. Factorization is not NP-hard. NP, yes, but not NP-hard. Okay. Yeah, so quantum Fourier transform, for example, is a very important tool. We will see this, okay? Like Hadamard transformation, for example, is also a Fourier transform. Later we'll see more general Fourier transform. Specifically in Shor's algorithm, we'll see Fourier transform. So Fourier transform is one important quantum algorithmic tool or primitive, okay, which people use often. Which also helps, for example, in phase estimation. Okay, there is a task called phase estimation. We will see that. Phase estimation is another important tool which is helpful in many places. Then there are quantum random walk algorithms. That's also a class of algorithms. Like what you are saying, right? Greedy algorithms, dynamic algorithms for classical case, right? This is a kind of, you can say, random walk algorithms, the type of class of algorithms. These kind of class of algorithms are helpful. Okay. Okay. Then there are other types, in the NISC era, there are these QAOA algorithms, VQE algorithms. They're also kind of class of algorithms. Okay, all right, any questions? Yes? Okay, so this is our analysis for Deutsch. Right, so as I mentioned, previously, if measurement result is 0, output is constant. If measurement result is anything other than 0, output is balanced. This is how our algorithm will work. Good. So this settles Deutsch. Okay? A task for which we see that quantum can do with one query, classical deterministic will need exponentially many queries, and randomized will need constant that depends on our error parameter epsilon. Okay. Okay. Now let us look at this search problem. Okay, search problem. Okay, search problem. What is the problem? Again, related to query. We have 4 bits in the database. Okay, so let's look at this problem because we may be covering this problem also in Qiskit, like actual design of circuit on a quantum algorithm or in a simulator, for example. There are 4 bits in the database. 4 bits in the database. Exactly one of them is a 1. So you could have 1 in the first position and 3 zeros, or 1 in the second position, 3 zeros, 1 in the third position, 1 in the fourth position. These are the 4 possibilities for the entries in the database. Agreed? Yes? We have to find out which one is the case. Agreed? This is our task now. 4 entries in the database, 4 bits in the database. It's a promise problem again. That is, there is exactly 1 1 and 3 zeros, but we don't know the location of the 1. And we want to determine what is the location of the 1. How many classical queries would you need? Huh? 3, right? You look at the first one, 0, second one, 0, third one, 0. Then you know the fourth one will be 1. Or in the meanwhile, you could see a 1. Like the first one may turn out to be 1 or the second one. But the point, in the worst case, you may need to see at least 3, because all 3 may turn out to be zeros. Correct? In the quantum case, we will see what you can do with 1 query. Okay? 1 query. So this is, you will see this actually implemented in the quantum circuit. Okay? When you run Cascade, you'll see it happening on a quantum computer or on a simulator. Okay? Then you will be able to appreciate the power of the quantum, right? Like, it's actually happening, right? It's not like some kind of a theoretical story, right? You'll see it's actually going to happen in the real world, right? You do 1 query and you get the answer. That means you know that quantum superposition is a concept of the real world. Yeah, it's not just a mathematical thing, correct? It's actually happening out there. Okay? Okay, so the circuit is as follows. See, many of our circuits look very similar if you note. The top 2 wires are zeros, Hadamard, Hadamard. Last wire is 1, Hadamard, BF. The last wire we will ignore and we will do something here. Yeah. Correct, but the number of, okay, so there are 4 locations, right? But the address of the location, remember, it's always x, f of x. X would be 2 bits. Okay? Right. So we start with 0, 0 and a 1. Hadamard we do. This 0 becomes 0 plus 1. This 0 becomes 0 plus 1. This one becomes 0 minus 1. Agreed? 0 plus 1, 0 plus 1, 0 minus 1. No issues. Now what we do, we simply write all this 0, 0 here, 0, 1 here, 1, 0 here, 1, 1 here. Agreed? Simply open up this bracket. This one we keep as it is. Now after BF and the regular analysis, phase kickback, etc., etc., usual stuff. What do we get? We get the value of f in the phase, correct? Remember? Always we are getting the value of f in the phase.
Sir, what does that tensor product 3 indicate there? H tensor product 3?
H tensor product 3 means h applied 3 times. H, H, H. No, 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 no. 4 bits. The important thing is these two represent the address of the location. The first 2 wires. Remember, it's a BF. BF takes X, B2, X, B parity f of X. F of X has, X has 4 possibilities. If X is 2 bits, it has 4 possibilities. Those are the 4 possibilities on the database. Locations. So, 4 possibility meaning we are not taking 3. For example, in the Deutsch case, we had 2 to the n entries in the database. We took how many wires? Top n wires to address the location and 1 additional wire. So, it's n wires to address the location plus 1 additional wire. So, the 4 is there, meaning 2 wires to address the location and 1 last wire that will help in our phase kickback. This one? Yes, exactly. This ket1 is basically helping us in this transferring the value of f to the phase, essentially in phase kickback. That is what it is helping us. So, -1 to the f00 will come here, -1 to the f01 will come here, -1 to the f10 will come here, -1 to the f of 11 will come here, with all this phase kickback etc. happening. Agreed? This one we are going to ignore. So, now what happens? You see, because of this, remember we have 4 cases. One case was that the first 0th location we had a 1. Every other location we had a 0. So, we will get a -1 to the 1 which is -1, here 1, 1, 1. Agreed? Huh? You see, there was one possibility, right? One possibility was 1 was on the 0th location and then 0, 0, 0. That will give -1 to the 1. -1 to the 1 is -1. -1 to the 0. What is that? -1 to the 0? 1. -1 to the 0? -1 to the 0? We'll get this. Agreed? Another possibility, 1 is in the second location. What we are going to get here? -1 to the 1. -1 to the 1. -1 to the -1 to the. So, you see -1 here, -1 here, -1 here, -1 here. These are the 4 possibilities. Agreed? Yes? These are the 4 possibilities we are going to get for the 4 different possible strings in the database. Okay? We got that. Fantastic. Now, we can note one thing. All of these 4 states here are orthonormal. Okay. What is the L2 norm of this? One, right? This is half square, 1/4, 1/4, 1/4, 1/4, 1/4, 1. So, L2 norm is 1 for all of them. What is the inner product of these two? Remember the formula we had for the inner product. Take the coefficient of 0, 0. What is here? -1. What is the coefficient here? What is the product? Product. -1. What is the coefficient here? What is the coefficient here? What is the product? What is the product here? Product. Add. Okay. Take these two, this and this. Product here, -1, -1, 1. gone. Let's take this 2, this minus 1, 1, 1, minus 1. So you take any pair, inner product is 0. So these are 4 orthonormal states, orthonormal vectors. So remember one thing, whenever we have a collection of orthonormal vectors, we can always distinguish them. Okay? We can always distinguish them. Okay? Why? So this is, actually this was also one of the questions that we were going to discuss in the tutorial yesterday, but we didn't have time. So this was one of the questions. But let me tell you, we also discussed the solution here. The solution is as follows. Okay. Let us say I have a bunch of orthonormal set of vectors vi's, n of them, let us say. I want to distinguish them. What do? Let us consider this unitary u. Remember, these are column vectors. vi's are column vectors, ket vi. Bra vi is row. Agreed? Bra vi is row. So you take the ket vi, do bra vi, this is the first row. Second row, bra v2, etc., bra vn. You get these vectors, and remember we have also, these are n vectors, small n vectors, each n cross 1, small n cross 1. No, conjugate is there, but this is just the whole vector is represented by v1, not the entry. Ket v1 represents that you are doing transpose and conjugate. Okay. Sorry, bra v1 for ket v1 represents that you are doing conjugate transpose. It is a dagger operation. But the point is, these are n cross 1 vectors. N cross 1 vectors. So they have small n number of entries. And there are n of them. So as such, they are in an n-dimensional vector space. They are in n-dimensional vector space, n vectors which are orthonormal. Okay. What happens? Take this u, unitary u. What is it formed as? First row is bra v1. Second row is bra v2. Nth row is bra vn. If you take that as a unitary, you take this u and multiply with ket vi. What are you going to get? Okay, let's do it this way. Bra v1, look at this. When you multiply, the first row will get multiplied with this column, right? To get the first entry. So when you multiply the first row with this column, what is it you are doing? Bra v1 with ket vi. What is that? 0. Because that is the inner product between v1 and vn. But they are, sorry, v1 and vi. But they are orthonormal. If I is different from 1, that will be 0. So first entry 0, all the entries, only the ith entry will be 1. All the other entries will be zeros. Agreed? So therefore this unitary, and why is this a unitary? Because it has orthonormal rows. Yeah? Because these are orthonormal set of vectors, we made them as rows. So it has orthonormal rows. Remember, our unitary was either orthonormal columns or orthonormal rows. So orthonormal rows, so it is a unitary. So therefore, uvi gives me this vector. So uv1 will have 1 here, all zeros. v2 will have 0, 1, all zeros. Like that it will have. So once we perform u, we end up with these vectors. Now we go ahead and measure. and we get our answer, I. Correct? Correct? So therefore, you will get answer I with probability 1. So therefore, this is a way to distinguish any orthonormal set of vectors in n vectors in n dimension. Distinguish meaning you should be able to perform some unitary and then measure in the computational basis. Remember the concept of measurement we had. You should be able to measure, and then you should be able to get a unique answer. Like if I want to distinguish between phi 1 and phi 2, I do the unitary, I get an answer. In case of phi 1 I should get 0. In case of phi 2 I should get 1. Now that is distinguished with probability 1. But if I were to distinguish it with probability 0.99 or probability 0.9 say, then what should happen? I should do the unitary. In case of psi 1 I should get 0 with probability 0.9. Maybe I can get 1 with probability 0.1. In case of psi 2 I should get 0 with probability 0.1 and 1 with probability 0.9. So there can be slight room for error, but that error should be small. Okay. That is what is called distinguishing with probability 1 minus epsilon. That means you are giving the right answer with probability at least 1 minus epsilon. Now the point is, whenever you have an orthonormal set of vectors, you can distinguish them with probability 1, no error, as long as you can rely on your gates being ideal. Okay. So therefore, what we saw that we have an orthonormal set of vectors, right? That is, in the circuit, after doing BF, here we got an orthonormal set of vectors. So we must have a way to distinguish them. We should be able to do a unitary here and measure so that we get the answer, correct answer. What exactly is that? So we can determine the unitary, but what is going to be the circuit for it? Exactly, right. We have to actually write what the circuit would be. So the unitary we can determine, mathematically we can determine. Remember the bra V1, bra V2, that one. Mathematically we can determine. But we have to also determine what is the circuit for it. So in this case, the circuit turns out to be actually this. That thing that I am writing here, dot, 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 is actually this, the red box. What is it? You do a Hadamard. This is called as a phase flip gate. It's the unitary given by this 1, 0, 0, minus 1. Phase flip gate. Okay. This is also phase flip gate. This is a controlled phase flip gate. This is Hadamard. What is a control phase flip gate? Control phase flip gate is similar to the control NOT gate. Remember we had the control NOT gate? If the first wire is 0, do nothing on the second wire. If the first wire is 1, flip the second wire. Control NOT. Similarly here we have the control phase flip. If the first wire is 0, do nothing on the second wire. Is it on, your mic? You just tap it and check. No, you press the bottom button for a while. No, you have to press it for a while. Now it's good.
Yes, sir. So my question is, like, if we want to do something, how we will know, like, what operations we should do, what circuit we should have? Does it come with experience or so?
Yeah. It will come with experience only.
Okay. So we have to do the math first and then go to the circuit, or we should, how is there is no way to. Like how do you approach any task? If
Yeah, for example, what you are asking is, suppose we have mathematically determined the unitary here, U here, right? But how we are going to decompose, figure out that this should be the circuit that does that,
yes.
okay? Now, this is not easy, frankly,
not easy.
okay? This and all will come. I mean, for Hadamard, for example, if it's like the Hadamard kind of unitary, you know what it is. Right?
Yes.
For particular gates, you know, like control, phase flip, control not and all, you know. But for the combination of gates, not easy, right? So this one will come, but at least you know that there is a unitary which I can perform which does it, right? And
Someone figures out some gate, they write a paper on it. Is it that tough?
no, no, not like that, I think.
Okay.
I know, I would say that, you know, you maybe propose a task, maybe a new task,
Okay.
and for which you exhibit a quantum advantage,
Okay.
right? You argue that, oh, quantum algorithms can do it fast and classical algorithms take time.
Okay.
Then you write a paper.
Okay.
Okay, the control phase flip gate is, now by the way, there are a lot of, these days there's a lot of applied conferences and applied journals also in the quantum case, in which case they may be writing papers on certain optimization of circuits and so on, right? Even for a given unitary, you know, the point is somebody has a circuit, but then somebody has a more optimal circuit for it, right, and so on. So those kinds of things are also there, okay? So control phase flip, as I said, was yeah. Yeah. Control phase flip gate is just this. Control on the first wire. If it is 0, do nothing. If it is 1, perform phase flip on the second wire, not the bit flip, right? That's the not is the bit flip. This is the phase flip. What is phase flip? If it is 1, you put a -1. All right. So this is what the overall circuit for this task is. But now you can see that in this circuit we have used BF only once. Correct? That means we have solved this problem with one query in superposition. One query in superposition. Classical algorithm would have taken at least 3 queries. Okay. This is kind of an instance of a small instance of what we'll see later, the more general Grover search. Here it is, you have 4 bits in the database, right? In the general Grover case, you have n bits in the database, and you have unique one, and you have to figure where it is. Interesting thing is, again, if you look at the classical case, you would need constant times n queries, omega of n queries. In the quantum case, you can do with square root n queries. Quadratic advantage.
Sir, I want to ask, like for every field there are some good forums where we have for our field like computer science and natural language processing, we know there is SIGIR, there is ACM transactions, there
Yes.
is IEEE.
Yeah.
So can you tell us, like for quantum, what are the good forums, which are the ideal papers which we can refer to in case we want to read about something? Like there are all kinds of forums, right? So what are the good ones?
Yeah. Journals, you're asking about journals, right?
Journals, conferences, or anything which are like worth referring, which should be taken as ideal and as your reference to.
Yeah. So you see, as such, for any field, doesn't matter which field, quantum, theoretical computer science, image processing, you know, AI, ML, whatever, any field, there is a concept of tier 1 journals, correct? So for that you can go to, there are standard websites, like core rankings, for example.
I know about that, but I don't know about this quantum field.
No, that's what I was, okay. So in any case, I'm saying any field, even theoretical computer science, any field, you can basically refer to what are the tier 1 journals, okay? And then for that, you just go to these websites and they will tell you which are the tier 1 journals in whichever field. Now, in quantum, there is a journal called Quantum. That is supposed to be a good journal. But people publish in regular venues, in physics, for example, PRL, PRX, Nature Physics Journal, PRA, all these are good venues. In computer science, IEEE transactions on information theory, ACM transactions, these are the venues which are there for theoretical computer science or computer science, but they also publish quantum papers. You can publish quantum papers there. If you look for just quantum only specific, it is this journal called Quantum. That is one nice journal. Okay. I think there is also recently one journal like ACM journal on quantum computing. I think so. Okay. But any case, Quantum is a journal you can try. And conferences, if you're looking for conferences, okay, there are a couple of conferences which are without publications, but still they are considered good venues because that is traditionally a lot of people go there, submit their, these are like talks, people give talks there, but you don't have published proceedings. It's called Quantum Information Processing, QIP, right? TQC, things like that. AQuiz, right? So these are the places you can just do a Google query, you know. Good venues for publishing in quantum field.
Google we can do, but now like there is so much misinformation also on Google.
Yes.
We need humans to tell.
Yes. That is true. That is true. That is true. If you ask ChatGPT, ChatGPT may give you wrong answers. You have to maybe refine the query, right? You have to do a bit of back and forth, and then maybe sometimes its answers become better, right? So, yeah. Okay? All right. So, I don't know, have you guys heard of these regular theory computer science conferences called Stock, Fox, Complexity, Soda and all that? But I think many of you are from the physics background, right? I think. Maybe. For physics, I think you might have heard of PRL, PRA, PRX, NPJ, etc., etc. Those things are there. For people in computer science, there are conferences called Stock, Fox, Soda, Complexity, etc. These conferences also accept papers in quantum. If you have a quantum paper, you can send it there. There are crypto conferences, Crypto, Eurocrypt, Asia Crypt. These conferences also, they accept quantum papers. TCC, you can submit there. Okay?
What to read as an I was more asking about what to refer to for reading as the
Reading.
not where I can submit a paper. I'm not that at stage, but I just
No,
want
I'll
to
tell
know,
you,
like,
for that what you can do is, you go to this conference QIP website. QIP for 2025, 2024, 2023 and all that. TQC. Okay? This is where many of the good papers that year in the field, they appear. I mean, people come and give talks.
Okay.
So that is where you can go.
Okay, sir.
You can start from basically QIP, TQC. That will already be good enough, because usually they have like combined QIP, TQC combined will have more than 200 papers in a year. So those are considered the top papers in quantum information, quantum computing, quantum cryptography from our field in that year as such. Okay? All right. Any more questions? Yes? So by the way, today we will have continuation. Yeah, today we will have continuation of the lecture. At least we will have 1 hour of lecture. Because we are trying to cover things that we will be covering in Qiskit. So one thing is this 4-bit Grover sort of, okay. We'll be looking at the Qiskit implementation of this. Another thing would be superdense coding. Superdense coding. So we'll also cover that. So you guys have the stamina for going to the next task now? Have it? Yeah? Good. Let's go. Okay. Okay. So now let us look at this task. We will look at 2 communication. See, till now we have been looking at these query complexity tasks. Now let us switch gears a bit, and now let us look at communication tasks. Okay, and we will see some kind of an advantage in the quantum case for these communication tasks. We look at 2 tasks. One is superdense coding, other is quantum teleportation. Okay, you might have heard of teleportation, right? Please raise hands who have heard of quantum teleportation. Okay, what is your impression of quantum teleportation? Meaning like how we see in Star Trek, right? You thought like that? Like a person will vanish from here, appear somewhere else. Okay. Yeah. Yeah. Yes. Anybody else? Huh? Data transfer. Huh? You have to long press the button below. Yeah.
Sir, teleportation means it's not any human transportation. It is for data transportation from one place to another place.
Okay.
That is what I read.
Okay.
Yes, sir.
Long distances.
Like wireless transmission of data. It is example.
Example, wireless transmission.
Yes.
Okay. Okay. Anybody else wants to say something? Okay. So now let us start with the task of super dense coding. What is the task? Alice and Bob, they are far away, okay? Two parties, Alice and Bob, they are far away. Alice has two bits, A and B. She wants to transmit these 2 bits to Bob. Agreed? That is a task. Alice has 2 bits. She wants to transmit those 2 bits to Bob. Classically, how many bits she needs to send to Bob to transmit 2 bits? Huh? 2 bits. Correct? Can she do with 1 bit? No way, right? In the quantum case, she can send just 1 qubit. 1 qubit. Okay? 1 qubit. And that will do the job. However, she will need the assistance of this entangled pair between Alice and Bob. Okay? EPR pair. Entangled EPR pair. This will be, yeah, EPR pair. I will explain. This EPR pair will be shared between Alice and Bob beforehand, before Alice gets the 2 bits A and B. Agreed? Then she will do some operations at her end and send 1 qubit to Bob. And Bob will do something at his end and recover the 2 bits A and B. Okay? It is called super dense coding because Alice is only sending 1 qubit to Bob for every 2 bits that she has. That's why it's called super dense coding. Okay. Now, the thing is this. EPR pair, right? What is an EPR pair? EPR stands for Einstein, Podolsky, Rosen. Okay? Einstein, of course, everybody knows. It doesn't need any introduction. Then there are other 2 co-authors of him, Podolsky and Rosen. It is named after these 3 people, EPR pair. What is it? It is this state basically. 1 over square root 2 ket 0 0 plus ket 1 1. Every 2 bits that Alice wants to send to Bob, they will be using 1 EPR pair. Remember, the EPR pair is shared beforehand, before even Alice gets the 2 bits that she needs to send to Bob. Correct. Then you will use 2 EPR pairs.
2 EPR pairs. Exactly. Then, like for 1 bit, I have, technically I have to send 2 times the communication, na? 1 for EPR pair and 1 for 1 qubit. But that we send it for once, like for remaining the communication we can do with that key, na?
Sorry, say again what?
So like,
no, if you want to send 20 bits, for example,
exactly,
you will need 10 EPR pairs. No, 10, you are saying how do we even share the EPR pair at the outset, you mean, right? Agreed. I agree with you that if you are also counting the communication needed to share the EPR pair, then you are actually sending 20. But the interesting point is the sharing of the EPR. Look, in the classical case, even if I allow you to send anything, okay, let's say Alice and Bob, from morning 7 o'clock, they can do whatever they want. Then at 1 p.m. they will get 20 bits. Alice will get 20 bits. Then after 1 p.m. still Alice needs to send how many bits? 20 bits in the classical case. It is not as if like, from 7 a.m. to 1 p.m. she can send something to Alice and Bob between. That will help her. After 1 p.m. when she gets the 20 bits. Agreed? Okay, here's the point. The experiment is as follows. Alice and Bob, Alice is here in Warangal, Bob is in Delhi. 7 a.m. they start. They can do whatever. 1 p.m. Alice will get 2 bits from outside. Somebody will come and give 2 bits to Alice. Then now how many bits Alice needs to send after 1 p.m. to Bob to communicate the 2 bits? 1 bit. No, I am saying classically. 2 bits. Agreed? If I give to Alice 20 bits at 1 p.m., how many she needs to send to Bob? Even if she has done something in the morning, does it help? Maybe they have exchanged zillions of bits before in the morning. Does it help? In the quantum case, they can exchange these EPR pairs in the morning. 7 a.m. to 1 p.m. they can exchange already. Then 1 p.m. she will get the 2 bits. After 1 p.m. she has to only send 1 qubit. If she gets 20 bits, she only sends 10 qubits. That is the advantage. There is a pre-processing part which is before 1 p.m. Then there is a post-processing after receiving the actual input. We are saving on the post-processing. I mean not the post-processing, the actual communication after getting the input is where we are saving. Pre-processing is there, I agree. But the point is in the classical case, even the pre-processing doesn't help. In the quantum case, at least pre-processing helps.
So you can save time at that particular moment when it's crucial.
Yeah, something like that. Yeah, total traffic will remain the same. But you can split it into a pre-processing stage and an actual online stage, as she is saying. That maybe after 1 p.m., after you get the data, you really need to do it fast or something like that. Okay? Is the EPR sharing. EPR sharing. EPR is this thing, this state. This state 1 over square root 2 ket 0 0 plus ket 1 1 is the EPR state. Remember, it is a 2 qubit state, correct? 2 qubit state. 1 qubit will be with Alice, 1 qubit will be with Bob. For example, it could be a pair of entangled photons. Okay? 1 photon is with Alice, 1 photon is with Bob. Yes, maximally entangled. This is maximally entangled. Exactly, there are 4 bell pairs. We can as such use any 4 of them in the protocol, but of course we have to accordingly change the protocol. But we will see it here with this bell pair. Okay? Yes.
If I want the communication to be secure, like the 2 bits or the 1 qubit that we're going to send from Alice to Bob, so is this EPR pair, is it supposed to be private to Alice and Bob, or can we just broadcast it across the channel?
No. If you are bringing security issues, then we have to be more careful. Depending on what we can give the adversary, what we cannot give the adversary at all. We'll have to be more careful there. So for now, we are not even looking at security issues. We are only looking at saving on communication. That's all. And our channels are also ideal. There is no noise, no loss, nothing. Simply, we are seeing if we have ideal channels, can we save on communication? Okay? All right. So now, superdense coding, what is the protocol? So here you see in the communication protocol we have given Alice and Bob, right? They are sharing this EPR pair, 1 qubit with Alice, 1 qubit with Bob. Later Alice gets this input AB, she sends 1 qubit to Bob. There are some operations that Alice does, some operations that Bob does. Here we have this kind of a vertical cut between Alice and Bob, right? But in the circuit model we are going to have a horizontal cut between Alice and Bob. Alice is on the top of the red line and Bob is on the bottom of the red line, because we have time flowing from left to right. So in the circuit model we are doing this horizontal cut between Alice and Bob. What is it? This is an EPR pair, okay, represented by this phi plus state. This EPR pair is shared between Alice and Bob. 1 qubit is with Alice, 1 qubit is with Bob. That's why the 2 wires, see, one wire is above the red cut, 1 wire is below the red cut. These are the 2 classical bits A and B that Alice receives. Both are bits. Because they are classical, we are representing them by double lines. First gate Alice does is controlled phase flip. Controlled phase flip. Another, but this is controlled on A. Another one is controlled phase flip controlled on B. Agree? She does these 2 operations and then sends this qubit to Bob. Okay? Her part of the EPR pair. After doing those 2 operations, she sends to Bob. Now Bob gets it. Then Bob does these 2 operations. A control NOT followed by hard MAT here. Then Bob is able to recover this AB. Here, control NOT. This is control NOT, this is control phase flip, control NOT, hard MAT.
Yeah, okay.
Yes?
Yeah, fine.
Okay. Now let us analyze this one, why it works. Remember, the communication from Alice to Bob is only 1 qubit. Only Alice is part of the entangled pair. Agree? Let us analyze. So earlier I was mentioning
Sending to Bob, sir, there in the circuit.
No, A and B are the 2 bit inputs that Alice has. Classical input. This wire is Alice's part of the 2 qubits. See, here are 2 qubits here. These 2 qubits. The phi plus state. This is the phi plus state. See, as such there are 4 wires. You see, 1, 2, 3, 4. You see this? 2 wires correspond to the EPR pair. 2 wires correspond to the 2 bits of input that Alice gets. Those are the 2 classical bits that Alice gets. She sends, yeah, but she gets, I mean, let's say that's her input that she wants to send to Bob. Those are the 2 AB. Then there are 2 wires corresponding to the EPR pair. Remember here, there are 2 wires here, 2 qubits for the EPR pair, and this AB is separate. Clear? She is sending. No, physically she is sending the qubit. No. Look, before this pair has been shared between Alice and Bob, this pair, you remember this has 2 qubits? One is going to be with Alice, one is going to be with Bob. This has been shared in the morning. Morning they share this one. Afternoon, Alice will send her part to Bob. Morning they share 2 photons. One is with Bob, one is with Alice. Afternoon she will send that her photon to Bob. Clear? Yes?
Sir, in that figure, like there is a crossover, right, in Alice qubit.
Yes, exactly. This is the part where she's sending it to Bob, because it's crossing the red line. You see, from here down here.
So the EPR pair is first sent, and then you have the or like how does
The
that
EPR
connect?
sending, has already been done here.
Okay.
This
So-
is not mentioned in the circuit. This is part of the pre-processing. So the EPR sharing has been done in the morning. This is happening in the afternoon. Yes. Yes. Second qubit. No. You are getting confused. 2 bits is separate. 2 qubits is separate. There are totally 4 wires. 2 bits is separate. This is A and B. 2 qubits is separate. You understand? 2 qubits is these two. You understand? Does it clear your question or no? Huh? EPR pairs. Qubits. Afternoon. Listen. The experiment is as follows. Morning 7 o'clock, Alice comes to her lab in Warangal. Bob will come to his lab in Delhi. Correct? Morning 7 o'clock. Then they will share EPR pair. It's 2 qubits. 1 qubit will be Alice with Alice, 1 qubit will be with Bob. They have done it from morning 7 o'clock to afternoon 1 p.m. After 1 p.m., somebody will come. Charlie will come from outside to Alice's lab. And Charlie will give Alice 2 bits.
2 input bits AB.
AB.
2 input bits AB. Yeah.
Huh?
2 input bits.
2 input bits.
AB.
Not qubits. But you can think of bits also as qubits if you want. No, I mean, just that they're in the computational basis, that's all it is. But point is, it's separate. What happened in the morning is separate. 1 p.m. separately Charlie will come and give you 2 bits. Then Alice has to now send these 2 bits that she has got from Charlie to Bob. How will do that? How will she do that? She will do some operations on her part of the photon. Remember the photon pair they shared in the morning. She will do some operation on her part of the photon and send that photon to Bob. Third and fourth wire are the 2 photons they shared in the morning. EPR pair. Look at this.
Okay, each one of them has 2 things with them or 1 thing with them?
No, basically, so the sharing of the EPR pair was not mentioned in the diagram. It happened earlier.
Yes, but it was a pair as in there were 2 entities with each of them or 1 entity with each of them?
1 entity.
So then why 2 wires?
Okay. Look, I am explaining, but I am repeating myself. So maybe why don't you take the mic and you explain it to her? Maybe that way it is better. Just take it.
Okay, so
Explain the experiment to her. I think she's confused about the experiment.
right. So in the morning itself, we shared a APR pair, you and me. Okay, and in the afternoon, say this guy gave me 2 bits, and I need to share them to you. And you're somewhere in the canteen having your.
I think your mic stopped. Press it, long press it bottom. Long press bottom.
Okay. So now, because we already have the shared EPR pair with us, so what I do is I perform some operations like the
It stopped again, I think. It's stopping.
Okay. So, and then what I do is I mean, I have one bit of the EPR pair, right, and you have one. So what I do is I change the state of the EPR pair that I have with me, and then I share that with you. And so yeah, you get it, and you apply the operation, which is the C naught and the hadmad, and then you get the state that he wanted me to share it with you. That's classical bit. Which are that is, yeah, I mean that is, yes. So the third line and the fourth line, that is the EPR pair. Yes. So the double lines A and B, those are the classical bits that he wanted me to share with you. You're clear with that? Okay, the third and fourth bit. Okay, so EPR pair is 2, right? A qubit. It's a 2 qubit state, right? So yeah, so basically one of them represents the bit that I have, the qubit that I have with me, the part of the pair that I have with me, and the other represents the part of the pair that I have with you. So I mean, the red line is like dividing between you and me, right? So one I have with me and one I have with you. You have it with you. So what I do is I apply some operation, which is the controlled phase flip and control not on the key, the part of the pair that I have with me, and then I send it to you. The crisscross represents that.
Okay. So let's analyze the circuit. I think it will become clearer, okay, as we analyze the circuit. Now, so what am I doing? I have these two, I have as such 4 wires, A, B, this third wire, fourth wire. What I do first, controlled on the first wire, do a control phase flip on the third wire. Then control on the second wire, do a control not on the third wire. Then after that, this is the 2 operations done by Alice. Then there are 2 operations done by Bob. Control on the third wire, not on the fourth wire, and Hadamard on the third wire. Agreed? 2 operations done by the Alice, 2 operations done by Bob. Fantastic. Now let us analyze what is happening. Before that, I just wanted to mention, remember we also saw the phase flip, right? This is the phase flip gate 1 0 0 minus 1. Control phase flip is if A is 1, apply sigma z on the second wire. Sigma z is the phase flip, control phase flip. The operations are like this. If it is 0 0, you don't do anything. Remember, first wire is 0. 0 1, nothing. 1 0, you are going to do a phase flip on the second wire. But the point is, there is phase flip only happens if the second wire is at 1. You see, there is a minus 1 here. So again, this nothing happens here. 1 1, now it will flip to minus 1 1. So that is the operation. Do nothing for these 3 guys, just 1 1, put a minus 1 on the front. Okay. Matrix is given by this 1 1 1, do nothing, minus 1 here. Clear? Control phase flip, great. Okay, now let us analyze what is happening here. Okay, I am going to keep this view, okay, right, because we need to see the circuit and the table. Okay, we are starting with initially what? AB is 0 0 0 1 1 0 1 1, 4 possibilities for AB. Phi plus state always starts with 0 0 plus 1 1, 0 0 plus 1 1, 0 0 plus 1 1. We are not keeping this 1 over square root 2 with us, okay, just for simplicity. Then what happens after the first gate is done? Controlled minus 1. Remember, control is on A. You are doing minus 1. On what? The third wire. That means when the first wire and the third wire both will be 1, minus sign will get introduced. Here it is 0 1, nothing will happen. 0 1, nothing will happen. 1 1, minus sign. 1 1, minus sign. Correct? First and third wire, you have to take into account carefully which wires you are doing control on. So that means if the first and the third wire both are 1, minus sign is introduced. That's what exactly happens here. Now here, control on the second wire and not on the third wire. Okay. Second wire, 0, nothing will happen. 0, nothing will happen. 1, there is the not on the third wire here. So, this third wire, this is the third wire. This 0 will flip to 1 and this 1 will flip to 0. Clear? Agreed? Controlled on the second wire B, because B is 1, the third wire 0 will flip to 1, 1 will flip to 0. Okay? Again here 0, nothing will happen. Here 1, third wire 0 will flip to 1, 1 will flip to 0. Agreed? Now as you were remarking, okay, we can see that now at this stage, after the control phase flip and the control not has taken place, we have actually created the 4 bell pairs. Right? We started with the EPR pair. Now we have created 4 bell pairs depending on the value of AB. For 4 different values of AB, we have 4 different bell pairs appearing between Alice and Bob. Okay? 0 0 plus 1 1, 1 0 plus 0 1, 0 0 minus 1 1, 1 0 minus 0 1. Okay. Now you can see that they form bell pairs orthonormal set. You see, what is the inner product between these two? 0. Clear? What is the inner product between first and the third? Correct? What is the inner product between second and fourth? First and fourth? You can check all pairs are orthogonal, and of course they are normalized with the 1 over square root 2. So it's an orthonormal set. So we know that once Bob gets both the qubits, which will happen right when the Alice is sent, Bob gets both the qubits, he gets one of the 4 bell pairs depending on the value of AB, but they are orthonormal. So therefore Bob can distinguish between them. Remember, whenever it's an orthonormal set, it can be distinguished. And once it can be distinguished, Bob can figure out the value of AB. So conceptually for us it is clear that Bob can do it. But again, precisely what will be the circuit? Circuit will be this: control not followed by Hadamard. Let us see whether what this circuit gives us. Any questions so far? What does this circuit give us? Control not. Now look at control not. Third, fourth. Control on third wire, not on the second wire. 0 0, nothing will happen. 1 1 will go to 1 0. Correct? But now what we have done, we have taken the 0 out, because it's 0 0 plus 1 0. Take the 0 out. 1 0 will go to 1 1. 0 1 will, nothing will happen. Again there is a 1, we take it out. 0 0 goes to nothing. 1 1 goes to 1 0. There is a common 0, we take the 0 out. 1 0 becomes 1 1. 0 1 becomes 0 1. Common 1, we take it out. So we have got all of this and all of this. Correct? Now a Hadamard transformation is taking place on the third wire. 0 plus 1 goes to this. This is also 0 plus 1. It is just written, but 0 plus 1 goes to 0. 0 minus 1 goes to 1 minus 0 goes to minus 1. But the minus doesn't matter. Now you measure. Remember, the global phase doesn't matter. So if you measure, you get 0 0 0 1 1 0 1 1. This is 0 0 is this 0 0. This 0 1 is 0 1. 1 0 1 0 1 1 1. Yes, please pass the mic to her.
So I have one question, like in the previous circuits we always had a wire and we trashed it. So here we don't have any wire and we are not trashing it. So what was the purpose of that wire and why is it not required in this particular circuit?
No, there we were using that wire to get the value of F in the phase. Remember the phase kickback.
Okay,
Here there is no F as such.
okay.
If you are thinking, yeah,
No, in general concept I want to know, not like
yes,
this circuit I understood, that
Ye-
circuit also I understood.
yes.
I just want to know like what is the purpose of that wire and in what kind of circuits we have to use that.
Yeah, that wire was basically used for phase kickback,
Okay.
which means getting the value of F in the sign.
Okay.
Okay. Here there is no F, so we are not using that. Any questions? But now you see what happened. You started with AB on the first two wires, you ended with the same value on the last two wires, 3 and 4. Correct? So this value got transferred to Bob by transferring only this qubit to Bob. Correct? 1 qubit of transfer amounts to 2 bits of transfer. That is why it's called super dense coding. Yes. So, can you just repeat the question?
How Bob will be knowing, sir?
Yes.
Suppose Alice has sent 0 1. How Bob will be knowing that?
Yeah, because look,
It is-
Alice has sent 0 1 means we are here, right? AB is 0 1. What is the value that Bob is getting?
But how he will know that? Is it 0 0 or 0 1 or what?
No, no.
She sent 0 1.
When Alice is having 0 1 here,
Hmm.
and when Bob has measured this, what is the value Bob is getting?
So he has to do all the 4.
Yes.
And then see.
See, Alice is doing these two gates on her end. Then she is sending the qubit. It's something like Alice is performing some gate on this photon depending on A, controlled phase flip. Then depending on B, she performs a control NOT on this photon. Then she sends this photon to Bob. Then Bob performs control NOT here and a Hadamard here and measures. Now what happens? The value that Bob is getting is always the same as the value that Alice is sending. That's how Bob is getting to know the value. Is it clear? Huh?
Alice has sent 0 0.
Huh. Bob will get 0 0.
Bob will get, but how do we know he will get 0 0 0 1 1 0?
How he gets to know? Because he measures. He measures, right? He will have 2 qubits. He will measure them. The outcome will be 0 0. Then if Alice is sending 0 1, outcome will be 0 1. If Alice is sending 1 0, outcome will be 1 0. Okay? Sorry, what?
In the last circuit,
Hmm.
there were 4 orthonormal vectors.
Yes.
So we did a unitary transformation to get the one of the values out.
Yes.
Here also same thing should be done, right?
Exactly. That is the unitary transformation. Control NOT followed by Hadamard. See, unitary transformation is there, but we have to also specify precisely what gates we are doing. We can write the unitary transformation mathematically, but we have to also specify what are the gates are doing, because that is what they will do in the real world.
Yeah, but that circuit was different.
Huh?
The previous circuit was different.
Yeah, because the unitary transformation was different.
Okay.
See, if there are if there are orthonormal vectors, depending on what the vectors are, the unity transformation is there. Here the vectors are different. Here the vectors are these 4. Earlier the vectors were something else. So it depends upon what the vectors are. Unity transformation will be depending on that. Not any set of orthonormal vectors, we will not have the same unity transformation.
Sir, here the 5 is they are sharing the EPR pair.
Yes, 5 plus.
Yeah, 5 plus. So that is this state, right? 0, 0 plus 1, 1. So instead of that, if we had used any of the other bell pairs, will these operations be the same or they will be different?
Different.
They will be different. Okay.
Yeah.
That phase. You have to decide, like design the circuit based on the EPR pair which you are having. That is the idea, right? Like before sharing.
Yes.
So that gives you security in some way. That gives you some security in some sense, right? Like this circuit will be decided only after you are fixing your EPR pair, and then you are sending, right? So that gives you some control over, say, somebody else stealing your data.
No, I don't know. I mean, the point is, if it, huh?
No, I am just asking. Like, with this, there is security also, right?
No. You see, when you're sending the qubit, Alice is sending the qubit to Bob. Is the adversary Eve able to do something to that qubit? Can it do some transformation on the? Is the channel between Alice to Bob, where Alice is sending the qubit to Bob, is that accessible by the adversary?
Yeah, he might be having access, right?
Now, once he has access, he can just do any operation on that.
Okay.
And if he is doing that operation, the whole protocol is gone.
Okay.
Because the state is no longer the same. Oh, it could be anything. Who knows what the adversary will do. So therefore, already the correctness of the protocol itself is a problem. Forget the security. If you give access to that channel to the adversary.
But he will be reading a wrong data, right? Like the chances are there that he will be reading a wrong data.
No, firstly, if he is having access only to the qubit that Alice is sending to Bob, that is anyway not giving any information.
Okay, yeah.
Because that qubit is just the same state, independent of what AB is. He will get information only if
the
he has
other
access.
qubit.
The other qubit also which is with Bob, but that adversary will not have access to. It's possible that in the morning also adversary did something when Alice and Bob were sharing, in which case also he may have. But the point is, in which case even the protocol will not work. Yeah?
Okay, yeah. Thanks.
Yeah. Okay. Any more questions? Yes?
Hello.
Yeah.
Sir, at the AB end,
Yeah, it is on.
yes sir, at the AB end, they are doing the operations of phase flip and control knot, sir. At LS end.
Yes.
But when it comes to Bob end, the circuit is different. But according to encryption or decryption, we need to go for the same decrypt to get the exact information.
No.
What, sir? I mean, I have doubt like that because the circuit should be reverse at least, but the same circuit should be used to retrieve the information at Bob end.
No. Why should same circuit? Firstly, these two wires are not even with Bob. Then
Okay.
how Bob can apply these gates?
My doubt is if I'm encrypt the data, like if we say EPR pair or something, if I'm encrypt the data by using one code, I use the same code to retrieve the data. Otherwise, I didn't get the data. That is the security reason, right? What is what? Okay. Yeah, we have two keys. Yeah. Decryption or? Okay.
No. Firstly, let me say one thing. Let us not even worry about encryption and decryption.
And nothing but how they are retrieving at the bob end. That is my question, sir.
Huh? Okay. Okay, so we saw superdense coding. In the afternoon, 1 p.m. we will, sorry, 3 p.m. we will meet and we will look into quantum teleportation. And if possible, start with the Simon's problem. Okay. Tomorrow morning, 11 a.m. we will have the Qiskit tutorial. Please bring your laptops. Tomorrow, I will send links for installation of Qiskit. Then you can install that also and come tomorrow morning. Okay. Using quantum protocols. Earlier we were looking at query complexity task for which we were finding advantage using quantum protocols. Now we will look at, so by the way, any questions related to superdense coding or whatever we did in the morning? We also saw Deutsch. Any questions about that? Good. Now, let us look at protocol of teleportation. Okay, teleportation. So, what is the task there? Okay, in teleportation, the task is as follows. Again, we have Alice and Bob. They are sharing EPR pair to begin with. Then Alice gets the input, a quantum state, psi, 1 qubit quantum state. It can be any 1 qubit quantum state. Alice gets it in a quantum register. Alice doesn't know what that state is. Alice doesn't know what the state is. It is just obtained physically like in a quantum register. Then Alice will do some operations at her end and then she will send 2 classical bits to Bob. I'm sorry. Okay, so she will send 2 classical bits to Bob and then Bob will end up with that quantum state. See, why it is called teleportation? Because what Alice is sending to Bob is only classical bits. However, a quantum state is getting received by Bob. You see this? If you see the number of possibilities of a quantum state, if you think of a quantum state psi as alpha ket 0 plus beta ket 1, alpha beta can be any complex numbers up to the L2 norm being 1. But there are infinite possibilities. Alice doesn't know what is the alpha, what is the beta. Without knowing that, by just sending 2 bits, 2 bits is just 2 bits of information. As such, if you want to see, if I want to encode alpha, alpha has infinitely many possibilities. If I want to even encode alpha, I will need infinitely many bits. Even to just describe alpha as such, if I want to do, I will need infinitely many bits. So I cannot do that. Agreed? So without even knowing that, the qubit is getting transported on the other side. That is why they are calling it teleportation. Get it? A quantum system is getting transported. A qubit is getting transported. Okay. Now, however, it is still requiring 2 bits of classical communication, okay, between Alice to Bob. Okay, so this is our task. Alice and Bob here are left hand side, right hand side. Alice and Bob here are up and down, as like in the morning. The Alice Bob cut is this green line here. Okay, the green line here is the green line here. So Alice and Bob are starting with the EPR pair. In the morning, 7 o'clock, Alice and Bob both do something and end up sharing EPR pair. 1 p.m. Alice gets this 1 qubit state psi as the input. Now Alice starts to do some operations. What is the operation? Alice will do a control knot from psi to first wire to second wire. Then a Hadamard here. Then she will go ahead and measure both the wires. Measure both the wires. She will get some classical outcome after the measurement. She will send those classical outcomes 2 bits to Bob. This going down means it is going from Alice to Bob. Bob gets the 2 bits. Bob performs control knot here and control phase flip here and outputs psi. Okay. Yes, yeah, mic please to him. Qubits. See, whenever a qubit you can, whenever you have any 2-state system, okay. For example, an electron can be in orbit 1, orbit 2. If it can be in superposition of orbit 1 and orbit 2, it is a qubit.
So what actually we send when we say that we are sending qubit from Alice to Bob?
We are sending that electron.
Okay.
See, sometimes you have photons. There will be 2 states, maybe polarization, okay, vertically polarized, horizontally polarized. Then at that time, if it can be in superposition of both the polarizations, then it is
okay.
Sometimes you have the other degrees of freedom, like spin degree of freedom. Spin up, spin down. Okay? A particle is in the spin up or spin down, but it can be in a superposition of spin up and spin down. That time you send the particle. It is in superposition. It's a qubit. Okay? It is actually a physical system. It can be a photon, it can be an ion, it can be a cold atom, it can be a, you know.
So how we store that thing, like let's say I send one photon from point A to point B.
Right.
So how we store that photon at point B, so that in future we want to work on that. Can we?
Yeah. So you're asking, like, if the photon goes there, how do we store it?
Yeah.
Because it's always moving.
Moving at, like, it's a photon, like it's a light actually that.
Yeah. So it's always moving. So what you do is you trap in a fiber.
Okay, and then keep it in.
Yeah, you keep it in a loop.
Okay.
Things like that.
Okay.
Okay. But it's amazing, you know, people, they are doing computing with photons, right? So photon is always moving at the speed of light. If you want to do a gate between two photons, you have to wait so that they get close to each other, and precisely at that moment you have to do the gate. Very difficult, and then they will also move. Huh? So it's a very non-trivial thing, right? Hmm? 2 bits here are sent over classical channel. Agreed. 2 bits here are sent over classical channel because they're classical information. But the point of teleportation is you can actually transport a quantum bit by transporting only classical information. However, again, you need the assistance of this EPR pair. Okay. Now, let us do
How is this not violating the no cloning theorem?
Very good question. The thing is this, the psi here vanishes. Cloning would have happened if there was a psi here and a psi here. Then cloning would have happened. What he's asking is, see, there is a no cloning theorem which says quantum information cannot be copied. You cannot just copy a qubit into 2 parts. But the point is, you are not copying. You are not copying. From here it is vanishing, here it is appearing. So it's not a copy. Okay? Okay, so now let us look at the analysis. Let us look at the analysis. This state psi is alpha ket 0 plus beta ket 1 here. Okay? It is normalized. Mod alpha square plus mod beta square is 1. Psi ket 5 plus is here. Correct? So our 3 qubits are like this, psi, tensor, ket 5 plus. So this is psi, tensor, 5 plus. Agreed? Yes? Actually, I want to keep the circuit and the analysis together. Is this visible? Huh? Not an issue, right? People at the back? Visible? Not visible? Huh? maybe you can come a little front, because so many seats are empty here. Or I'll zoom then, but the point is if I zoom, we'll miss the circuit. Okay? But anyway, let's remember the circuit. I'll keep going back and forth. So it's the control node followed by Hadamard, okay? And then measurement. Now it's better? Okay. So now we have this, right? Starting 1 qubit here, our input state, and this is the EPR state pair. We simply take the 1 square root here and then just expand, right? 0 0 0 alpha, 0 1 1 alpha, 1 0 0 beta, 1 1 1 beta. Okay? Expand. Good. Then we do a C naught that is there in the circuit. C naught is what? First wire to second wire. Control on the first wire. If it is 0, nothing will happen. 0, nothing will happen. 1, this thing will flip. So 0 goes to 1. 1, this thing will flip. 1 goes to 0. Agreed? Control not, control on the first wire, not on the second wire. Remember, we have to do this on every element of the superposition, because everything is happening in the superposition. Good. Now we are rearranging. 0 0 we take out here, 1 1 we take out here, 1 0. Oh, wait a second. Sorry. Then we did a Hadamard. Remember? Hadamard. Hadamard is on which wire? First wire. Okay? So 0 goes to 0 plus 1. This 0 0 as it is. 0 goes to 0 plus 1, 1 1 is as it is. 1 goes to 0 minus 1, 1 0 is as it is. 1 goes to 0 minus 1, 0 1 is as it is. Agreed? Yes? Okay, Hadamard is done. Now we are rearranging. Okay? Now we are rearranging. Algebraic manipulation. 0 0 we'll put in front. Then what do we have? Alpha 0. There is another 0 0. Where is another 0 0? 0 0. Beta 1 minus. Sorry, plus 0 0 1. So beta is plus only. Beta 1 here. Agreed? Yes? We are just taking the 0 0 out here. We are getting alpha 0. 0 0 out here, beta 1. Agreed? Then what we did? 0 1 out. Where is 0 1? 0 1. Alpha 1 here. 0 1 beta 0. Agreed? 1 0. Where is 1 0? Here 1 0. Alpha 0. Then there is 1 0 minus beta 1. Agreed? 1 1. Where is 1 1? 1 1 alpha 1. Then 1 1 minus beta 0. Agreed? Simply we just rearrange the terms. Take the first two wires, whatever is the value, we take it out. Okay? Algebraic manipulation. Now Alice measures the first two wires. Recall the concept of partial measurement. Recall the concept of partial measurement. Remember, she is not measuring all the three wires, only the first two wires. First two wires she measures. What is the probability of getting 0 0? 1 by 4. Probability of getting 0 1? Probability of getting 1 0? Okay. Probability of getting 1 1? 1 by 4. all the 4 distinct possibilities are obtained with exactly the probability 1 by 4. Now if she gets 0 0, what is the state of the qubit on the third wire? Huh? Alpha ket 0 plus beta ket 1. If she gets 0 1 on the first 2 wires, what is the state? Alpha ket 1 plus beta ket 0. If she gets 1 0, alpha ket 0 minus beta ket 1. If she gets 1 1, alpha ket 1 minus beta ket 0. This is the state obtained on the third wire depending on what Alice gets on the first 2 wires. Now she is sending this value to Bob. Bob gets to know. So Bob gets to know as such that these are one of the 4 possibilities. But Bob doesn't know what is alpha and beta. Remember that. Bob only knows which of the 4 possibilities occurred, but Bob does not know alpha, beta. However, Bob can do some corrections now at his end. What is the correction? See, Bob is doing control not, control phase flip, correct? Control not depending on the second wire, control not. Like there are 2 wires here, right? Measurement outcomes. These are 2 measurement outcomes. The first one, the second one. The control not is with respect to the second one. Control phase flip is with respect to the first one. Agreed? Okay, now let us look what is the state on the third wire after measurement. That is what we have just now found. Okay, the 4 outcomes are obtained. The state on the third wire after measurement is this that just now we saw here. Agreed? Correct? Fantastic. Now probability of outcome 1/4, 1/4, 1/4. State after C naught. Now let's look at the state after C naught. C naught is with respect to the second wire. Okay, 0 0, nothing will happen. So this state is as it is. This state is as it is. Agreed? 1, what will happen? 1 will go to 0, 0 will go to 1. So alpha ket 1 plus beta ket 0 goes to alpha ket 0 plus beta ket 1. Flips. Agreed? Fantastic. When it is also 1 here, alpha ket 1 minus beta ket 0 goes to alpha ket 0 minus beta ket 1. Correct? Any issues? Good. Now there is a control phase flip. Control phase flip on the first wire. First 2 it is 0, so nothing will happen. This is, we are now looking at this operation. This will go as it is, this will go as it is. Agreed? This will go as it is. This one control phase flip, because 1 it is here, the 1 here will change the sign. Minus will come plus, minus will come plus. Agreed? So now you see here, everywhere alpha ket 0 plus beta 1, alpha ket 0 plus beta ket 1. See, just after Alice had measured and sent this information to Bob, Bob had these 4 different states. But Bob was able to do the correction and bring all the 4 states back to the right state without knowing alpha beta, just by control not, control phase flip. Correct? Any questions? So finally the state that Alice started with got teleported to Bob. That is teleportation, quantum teleportation. But, you know, okay, if you try to think of it like, oh, suppose I have a particle. The particle vanishes here and I send classical information and the particle appears there. It is not quite like that. You know why it is not like that? Because a particle is actually in a several different types of degrees of freedom. Here we are only considering one particular degree of freedom, 0, 1, which could be spin, which could be polarization or something. But the point is, a physical system is living in a much larger dimensional Hilbert space. For example, there is a position degree of freedom. There is momentum. There are so many other physical quantities associated with that particle. We are only transporting one such thing, maybe spin. But we are not transporting even other things, other properties of that physical system, right? Position, momentum, this, that. So it is still not like a physical system is vanishing from here, appearing there. It is not like that. It is one particular degree of freedom. One particular degree of freedom, 0, 1. Maybe it could be spin or something. The information there which is in superposition, that get transported to the other side. So it is more subtle than we think that, oh, just some physical system vanishing here and appearing there. Because that physical system will actually have, you know, in order to fully describe the physical system, you have to describe so many things. You cannot just describe using, oh, it's a state in a two-dimensional Hilbert space. It's not a state in two-dimensional Hilbert space.
So now we have a copy of two particles with the same freedom, degree of freedom which we are measuring.
No, it is not the copy. Exactly the same question here.
In that particular degree of freedom.
No, it is still not a copy because it vanishes from Alice's end. No, the particle will be there, but the measurement has been done in that degree of freedom.
So the states collapsed.
Huh?
State collapsed when we measure.
There is a state collapse. In that, like spin, for example, in spin Hilbert space, the state will collapse. But it may still be in superposition, for example, in a position Hilbert space. Okay? Things like that. Okay? Okay. So, this is teleportation. Any questions? At least now if somebody is telling you quantum teleportation, you can at least tell them what is quantum teleportation, right?
Sir, how it is different from that entangled pair of photons? Because in that also, whatever we are doing here, we can measure it at the other pair.
No, you see. Entangled pair is a different thing. Look, here we are not copying. We are not saying whatever is happening in this particle, same thing is happening in that particle. No. We are actually sort of transporting this qubit there. Okay? It's not about kind of creating two correlated qubits or anything like that. The correlated qubits are actually the EPR pair, which we are using in the protocol. Okay. Using the EPR pair, we are teleporting a separate quantum system, 1 qubit quantum system from Alice to Bob. Teleportation is different from creation of entangled pairs. Okay. So, we have seen now today two communication protocols. Quantum communication protocols. Now, we will go back. Now, we covered these two things because these things will also be covered in Qiskit. Superdense coding and this other thing that we saw, 1 out of 4 search problem, right, in the morning. There is a single 1 out of 4 bits, correct? In the morning we saw, remember, single 1 out of 4. So those things will be covered in Qiskit. So that's why we did the theory, so that the Qiskit programming part we can do tomorrow. Good. Now we will come back to the Simon's problem, which is another problem in the query complexity world. Okay? Query complexity world. Let us begin by understanding what the task is. Any questions about superdense coding teleportation? Do you have a question? Huh? No, she has a question.
Now I got clarified.
Clarified.
Yes, sir.
Ah, you were asking question about teleportation.
Yes, sir. Now I got clarified after discussing.
Flip and then CNOT.
Yes, sir.
And
That is what I am asking morning, sir. In superdense coding, we are having this circuit, sir. In the one paper, they mentioned, sir, so that only we can reconstruct. We can perform teleportation. So that's why I'm asking morning, sir. I got half clear. That's why I'm asking, sir.
Okay.
So now I got clarified, sir, because of the circuit. Second circuit, the exact opposite of the morning one, sir.
Ah,
Yes, sir.
teleportation is opposite of superdense coding.
Yes, sir.
Is different.
yes, sir. Here at the Bob side, for Bob output to apply again the reversal, then we are going to have.
Yes, sir. That is what I asked morning.
No, it is still different. Huh?
They mentioned
You are saying control not control, sorry, control phase flip, control not,
after this one,
then control phase flip, control not,
flip this one, sir.
then here it is control not hard mart.
Sir, for superdense coding, we add the.
It is control not hard mart, but it is a reverse order. Eh?
Reverse of that one, sir.
See, these are completely different tasks.
They mentioned.
So by it case, so maybe a coincidence like that. Huh?
Yes, sir. They mentioned one condition, sir. I understood very well, sir.
Very good.
After this only, sir. That's it.
Very good. Very good. Okay. So now let us go to another one. Simon's algorithm. Okay? Simon's algorithm what is the task that we have? Task is there is a function f. Okay? Function f. Now its input length is also n bits, its output length is also n bits. In Deutsch, input length was n bits, output length was 1. Now input length is also n bits, output length is also n bits. And what is the condition? Okay. Condition is as follows. Okay, let us take the example. Maybe, with the example, condition will become clearer. Here is an example. X is here, f of x is here. Okay, 0, 0, 0, this is the input, output is 1, 0, 1. Okay. Where is 1, 0, 1 again? Here. 1, 0, 1. Correct? What is the input here? 1, 1, 0. If you look at the bitwise parity of 0, 0, 0 and 1, 1, 0, what is it, that one? Huh? Bitwise parity means here, you see, if you have n bit input here, n bit input here, x1 through xn, y1 through yn, you do bitwise parity, x1 parity y1, x2 parity y2, xn parity yn. So 0, 0, 0 parity 1, 1, 0 is 0 parity 1, which is 1, 0 parity 1, which is 1, 0 parity 0, which is 0. So the parity of this and this is 1, 1, 0. Agreed? Okay. Let's look another example. Here is 0, 1, 0. Where is 0, 1, 0? Here. What is the input here? 0, 0, 1. What is the input here? 1, 1, 1. What is the bitwise parity of 0, 0, 1 and 1, 1, 1? Huh? Ah. 1, 1, 0, right? See, 0, 0, 1, 1, 1, 1. 0 parity 1 is 0 parity 1 is 1 parity 1 is, so you get 1, 1, 0. Let's take another example. 0, 0, 0. Where is 0, 0, 0? Here. Input is 0, 1, 0. Here is 1, 0, 0. What is the bitwise parity? 1. So what are we finding? Let's take another example. 1, 1, 0. Where is 1, 1, 0? Here. 1, 1, 0 here. 0, 1, 1, 1, 0, 1. What is the bitwise parity? So what is the... Yes, let me just say what is happening here. The thing that is happening is that take any value of f of x. There are exactly two inputs which are giving me the same value. It's a 2 to 1 function. Exactly two inputs give me the same value of f of x. And those two inputs, if I do the bitwise parity, it's always equal to 1, 1, 0. Yes. All the inputs. So any value of f of x, if you look at the two values of x which give me the same value of f of x, the two values of x, if I do bitwise parity, I am always getting 1, 1, 0. That is what we have seen in the example. Agreed? So that is the promise that is available to us. It's a 2 to 1 function such that whenever f of x is the same for x1 and x2, then the bitwise parity of x1 and x2 is the same string s. That is the promise available to us. We have to find s. That is a task. Yes. Yes. There could be many such. But different s, exactly. Pre-images, exactly. Exactly. So we have to find that s. That is a task for Simon's algorithm. Formally, we can write it like this. There exists an S in 0, 1 to the n, which is n bit string, such that for every xy n bits, such that f of x is equal to f of y. Both of them are mapping to the same value. Then bitwise parity of x and y is S. So this thing that f of y equal to f of x is equivalent to x parity y is equal to S. Agreed? Our task is to find such an S. Now, classical algorithms. If we try to run classical algorithm, deterministic algorithm, what we can do? Look, in the database, sorry. In the database, there are 2 to the n entries, correct? Each entry is n bit. 2 to the n entries, each entry is n bits. And we are supposed to determine S. What we have to do? We have to keep looking. 2 times the same value should appear. Like in this table, we have to keep looking. 101, again 101 should repeat. Correct? Yes, exactly. Exactly. So, keep looking. Worst case, we have to keep looking half the entries. We keep looking, no repetition. Only when you look at half the entries, plus 1, there is repetition. Agreed? Half the entries may be just distinct. Keep different, like here, different. Right? So it is exponentially many queries we have to do to the database. Agreed? 2 to the n divided by 2. Exponential in small n. If you look at classical randomized algorithms, okay, remember in the morning we said for Deutsch, we said deterministic algorithms need exponentially many queries. Randomized algorithms, constant number of queries. Now, let us try randomized algorithm on this. Randomly we pick a few entries. We should see 2 entries being the same. How many times you have to look? Huh? Yeah, but how many times? You see, I have 2 to the n different entries are there in the database.
Okay, so you want one like 100% result. You
No,
don't
not
want
even
any
high
error
probability. High probability. Let's say 0.99 I want.
So 100 iterations are enough.
To get what? See the double entries?
Yes.
Repeated entries?
Yes, you will have a very small probability
Look,
that it will go
half
wrong.
the entries are distinct. Half the entries are distinct. Suppose I have 64 entries in the database. 32 of them are different. Then they are repeating. But somewhere they are repeating. I should be able to see a collision. That is one entry, another same entry.
30 plus time.
Correct. Suppose I have 128 entries in the database. 64 of them are different. Then they are also repeating. Remember here, there are 8 entries here, right? But 4 are different. 1, 2, 3, 4 different. Huh? 2 to the power n by 2. Why 2 to the power n by 2?
No, sir.
2 to the power n, you are saying 2 to the power n by 2 in the exponent, or 2 to the power n divided by 2? Ah, that is like this one, you mean? Huh?
No, sir. Sir, the probability is very small that the probability is very small that we may get different values. We may get same value, and if we keep repeating the experiment, the probability keeps on reducing.
No, that's why I'm asking you. Suppose I want to spot with high probability, let's say probability 0.99. I want to spot 2 entries which are the same. How many queries I have to do to the database? Huh?
Yeah, half.
Half.
Total entries divided.
No, that is for the deterministic algorithms. For randomized algorithms, how many I have to do? Suppose I'm randomly looking at entries. 2 to the power n minus 2. Minus 2 like in the exponent or no? Outside. Outside minus 2 is not helpful. 2 to the power n, huh? In the exponent. But that is deterministic. I'm asking randomized. Okay, here's the question. How many people are here? 50 people are here. Approximately 50 people are here. Everybody has a birthday. Agreed? 1 out of 365 days are there. Correct? In a year, 365 days are there. Everybody has a unique birthday. If I put a number, say 20th February, then it will be some number out of 1 to 365. 15th March, some number. What is the probability? Now there are 50 people. Do you think there will be 2 people whose birthday will match? Okay, raise hand how many people think that there will be at least 2 people whose birthday will match. Raise hands. Huh? 1 minus epsilon. 1 minus epsilon probability, you mean? No, that's correct. I am saying, let us say I want to argue that with probability 0.99, there will be 2 people here whose birthday will match. Is that correct? But there are only 50 people, there are 365 birthdays. There are 365 birthdays. Only 50 people are here. You think they will match? Huh? Do you need like half of them? 365 divided by 2, something like 180 you need? You need 180 for matching birthdays? 50 will match already? Why 50 will match? Yes, but there are 365 days. So with 365 days, how many people do you need in a room such that with high probability their birthdays will match? Huh? How many people do you need in a room such that with high probability their birthdays will match? Huh? Half plus 1. That means 360 divided by 2. 182 something. Plus 1. 183. Like that you are saying. Huh? 184 like that you are saying. How many people think that we need 184? Raise hands. How many people think that Having 20 people in the room is enough. Huh? No, probability 0.99 I want. Hmm? No, that is correct. 184 will be enough. But I am asking, is much smaller number. Like is 20 enough? 32. From where 32 is coming? Huh? No, I am asking. You see, 184 I agree. But if I say, oh, I have 10 people in the room, is there a high chance that their birthdays will match? Yes? 10 people only. Who said? Somebody said yes, no? Okay. If I have 20 people, you think their birthdays will match? 30 people? No, probability increases. I want probability to be 0.99. You think 30 is enough? 40 is enough? 50 is enough? 50 is enough? No. I want month also to match. Okay? You think 50 is enough? 50 people are there in this room. You think birthdays will match or not? What is the high chance that some two people will have their birthday matching? Huh? You think in this room there is a high chance that two people will have their matching birthdays? You think there is a high chance? Huh? Yes? You are saying yes. Right? So maybe let's do the real experiment. Huh? Shall we do that? Huh? No, because as such, okay, let's just do a very quick raise of hand. If we find two people matching birthdays, how many people will be surprised? Raise hand. Yes, just this room. Fantastic. Okay? So many people will be surprised. Let's do the real experiment. Okay? You please start for your birthday. Okay, we have to remember it a little bit, so that we can see. Oh, at least, oh no, let's do it this way. Let's do it this way. If somebody says the birthday, if somebody else has the same birthday, they will just raise the hand. How about that one? Correct? Let's do it. Huh? No, exact. It has to be exact. Not plus minus 1. Okay, let's start. Anybody matching? November 28. This one. Not matching. Hey, everybody, you have to be a little bit watchful, whether it's matching or not. People are watching, right? You just slowly, one by one. April 2nd. Oh, so close already. No, that's okay, that's okay. 8 September.
September 10th.
December 10th.
Oh, you see he's matched. You see he's matched. You see this? Huh? We did the live experiment, right? And it matched. So you see, huh? That is called as the birthday paradox. Huh? Search is at random. Correct. So what happened? Actually, if you have 2 to the n distinct values, or capital N is 2 to the n. For us, capital N is 365. If you have capital N distinct values, then if you have square root of that, what is square root of 365? Approximately less than 20, because 20 times 20 is already 400, less than 20. You can expect, if you have 20 people, already the birthdays will match. In fact, if you see, we are asking, I think we have finished only 20 people, right? We didn't finish 50 only. Yeah? That is the thing. What is the math behind that? We have to do the analysis, okay? But that will take time once we get into the analysis of birthday paradox. But the point to be taken for now is that even if there are square root n random entries, there they will match, the values will match.
So what is the principle or intuition behind that? Not the full analysis, but at least what is the key to that?
The thing is this. I mean, this is basically due to randomization. Because we're randomly picking. We're randomly picking square root n entries. See, as your number of entries grow, your set that you have collected grows, then the probability that you don't get matching entries also keeps reducing. And then there is this trade-off. And then the trade-off hits exactly at square root n, the correct thing. So the thing is, due to randomization, it basically means that if I have 2 to the n entries, which means there are 2 to the n over 2 distinct entries, which means if I randomly select, I will get matching entries in square root of 2 to the n, not 2 to the n or not 2 to the n over 2, but square root of 2 to the n. That is the birthday's paradox. Still it is exponential, agreed. Square root of 2 to the n is 2 to the n over 2, but n over 2 in the exponent. But that is still exponential. What?
2 raised to n divided by 2. Here in this example, we have 2 raised to n divided by 2 distinct values.
No. We had 2 to the power n, yeah, but not in the exponent. 2 to the n we had these many distinct values.
Yeah, then the square root of that is not this one, right?
Square root is this much, approximately. Now, how does it matter?
Yeah, approximate only, right?
That's okay. Anyway, I am talking birthday paradox also, there is a constant factor on top of it. It is not exactly. For example, if you have 20 is the square root n, right? But if you want probability to be very good, safely, very, very close to 1, you make it 30 people. Then it will be good. 30 people will be good. Okay? Probability. Probability of matching birthdays. Matching birthdays. So if you have 30 people in a class, there is a very high probability that 2 people will have matching birthdays. That is called as birthday's paradox. Because many people find it surprising. Right? We just now saw here also. Many people found it surprising. Okay. But nonetheless, even if you do that, it's still exponential. So even classical randomized algorithms will take exponential number of queries. Because otherwise what can you do? You see, if you think about it, it's not a full proof, but if you see just randomly pick entries, you have to wait for a matching entry. But Butler's paradox is telling us we will need square root of 2 to the n. Much smaller than this you cannot do. Square root n is enough, but much smaller than that you cannot do. So unless you have matching entries, you have not seen the collision, right? If you have not seen the collision, how will you know what S is? Because S you can only find if you see a collision and then you take the pre-images and you do bitwise XOR. Agreed? So in order to see, you have to at least see a collision, right? So therefore, this is not a full proof, but this is little bit just to get an idea. Point is, even classical randomized algorithm will take exponential time, exponential number of queries. Now here quantum will do it in polynomially many queries. So now you see the advantage. Quantum is now giving an advantage even over classical randomized algorithms. Morning we saw advantage over classical deterministic algorithms. Now we are seeing advantage over classical randomized algorithms. Okay? Okay, so that defines for us what the task is of Simon's problem, right? Then we look at the algorithm analysis and all, but we now take a break, okay, at 4. We take like maybe 15 minutes break and then we'll resume and then we look at the analysis. Okay, so the task is clear to us, right, for the Simon's algorithm. What is the task? Now, circuit is as follows. We start with n wires all in zeros, another n wires all in zeros. The first n wires we do Hadamard on every wire. Then we do a BF. Remember the BF here will take the first n wires as the address and the last n wires where it has to give the function value. Correct? Then again Hadamards on the first n wires, measure, ignore the last n wires. This is the circuit. Agreed? Now let us look at the analysis. Okay, remember circuit is we are doing Hadamard on the first n wires followed by BF. Okay. Okay, so to recall, BF action is like this. X is n bit, Y is n bit. X and Y go to X and Y parity f of x. Correct? Usual action of BF. But in this case, input is also n bit, output is also n bits. So therefore, X is also n bit, Y is also n bit. X, Y parity f of x. Clear? Fantastic. Now we started with these 2n bits all in zeros. First n bits we did Hadamard tensor n, that is Hadamard on every wire. What are we getting? Our formula, remember all zeros goes to this uniform superposition over x using the formula for Hadamard tensor n. All zeros goes to uniform superposition over x. This is the normalization condition. 0 to the n is as it is. Now what happens? BF, x goes to as it is, 0 goes to f of x. Remember BF acts, x 0 will go to x, 0 parity f of x. 0 parity, 0 when I say 0 it's 0 to the n zeros, but n zeros parity f of x is f of x. Whenever we say parity, it is always bitwise parity. Okay? Parity of n bits is bitwise parity. Get x. Get x. Okay? So now the Hadamard. When the Hadamard acts, it comes here. Okay? It acts here. Sorry, BF acted, right? BF we got, no issues here. Then the Hadamard acted. Remember another Hadamard on the first n wires. So we acted Hadamard. Here is the Hadamard. Use the formula. Hadamard tensor on x is summation y minus 1 to the x dot y y. That is the formula for Hadamard tensor n on x. Summation y minus 1 to the x dot y get y. Agreed? This is this now. Fantastic. F of x is here. Now let's look at this. Okay, this is a little bit cutting here, but we'll go to the next one. Okay, so this one is this, right? What we are now going to do is we are going to just change the summation order. Okay, y will go here, x will go here. Now once we have changed the summation order, we are getting y coming out, get y, correct? And now this minus 1 to the x dot y is here, f of x is here, and then summation x, correct? Okay. right? We simply change the summation. So y came here, x went here. Because with y we can collect this y here. X is here, minus 1 to the x dot y, f of x. Okay? Very good. Now we are going to measure y, the top n y's. Remember? We are measuring. Probability that we get an output y is L2 norm square of this vector. Remember that? For partial measurements, the probability was L2 norm square of the associated vector. So probability of getting y, output y is L2 norm square of this. 1 over 2 to the n is here. L2 norm square of this. Fantastic. Now what we are going to do is, we are going to note the following. Remember, okay, let's take the case when, so we are taking the case when every value f of x has exactly 2 pre-images, right? So z is there are 2 pre-images, xz and x prime z, both mapping to z. xz, f of xz is also z, f of x prime z is also z. 2 pre-images of z. So now what is happening? We are writing this as z. Z is in the range of f now. Okay, x, instead of f of x we are writing z. Z is in the range of f. There are 2 different x's here, minus 1 to the xz dot y plus minus 1 to the x prime z dot y. Both of them are giving z. Agreed? Right? Instead of writing x f of x, we are writing z and the pre-image. But there are 2 pre-images, so we are collecting both the pre-images. Agreed? Yes? Any question? Huh? Not getting. Okay. Shall we start from the beginning or just the pre-image step? No, for her, till this point it is clear, or even we should start from the beginning? Recap from the beginning. Okay, here. Circuit is this. Okay? We are taking n wires, doing Hadamard. N wires at 0. BF, then n Hadamards measure. Huh? We will trash all those n, bottom n wires. What is the action of BF? It takes xy to x, y parity f of x. Usual action. But at this point, y is also n bits. Because f of x is also n bits. X is also n bits. So this is the usual action. That's why we have n bits here, n bits here. So now we are starting with zeros and zeros, zeros and zeros. H, we applied the H on the first n zeros. Use the formula for H tensored n acting on zeros. If you use the formula, we get this uniform superposition over all x. Okay? This we have seen even in the Deutsch. Uniform superposition over all x. This 0 is as it is. Agreed? This is with the first action. Now we applied BF. What did BF do? X, y goes to x, y parity f of x. So x0 will go to x parity x and 0 parity f of x. 0 parity f of x is just f of x. Then we applied n Hadamards. N Hadamards on this wire, n wires. So it will be H tensored n on x. Agreed? F of x is as it is. Use the formula for this. Remember there is a summation x here. This summation remains. Then you use the formula for this. That introduces a fresh summation over y. minus 1 to the x dot y, y. This is from the formula for h tensor n. Okay, maybe we have the formula here also. No, we don't have. Okay, it was there in the previous, this one, Deutsch. That we did. F of x is staying as it is. Now what we did, we exchanged the two summations. Y goes here, x goes here. Okay. So when we exchange the two summation, y came out. With y we collected this y here. X came inside. This minus 1 to the x dot y is here. F of x is here. Agreed? So till now we are okay. Any questions? Yeah? Good. Now what we did, we measured the y, top and y. Remember? We are measuring y. The probability that we get an output y is, remember our partial measurement analysis, probability of getting y was L2 norm square of this thing. So it is the L2 norm square of exactly the same thing, minus 1 summation x minus 1 to the x dot y f of x. L2 norm square, of course this 1 over 2 to the n also will be there. Agreed? This is the probability of getting y. Now what is happening, we have to little bit carefully see. What is, here is a summation over x and then there is f of x. We are rewriting the summation in a certain way. Instead of f of x, I am writing f of x equal to z. Correct? Now there are two x's which are giving me the same value for f of x. So there are two x's which give me the same value z. I am calling the two x's which give me the same value z as xz and x prime z. Xz and x prime z. I am collecting the two terms together. So there is a z minus 1 to the xz dot y plus minus 1 to the x prime z dot y. That's all we have done till now. Okay. Any questions? All good? Very good. Now what are we doing? We can note one thing. We have this promise, remember? Xz parity S is x prime z. Bitwise parity of xz and x prime z was S. But that is the same as bitwise parity of xz and S is x prime z. See, if A parity B is C, then A parity C is B. It is exchangeable. So x prime z parity S is xz parity S is x prime z. That's what we are putting instead of x prime z, xz parity S. Agreed? We put that one. We get rid of one variable. Now we can use another formula which is this: A parity B dot C. Remember the dot, inner product modulo 2, bitwise product addition mod 2. It's the same as A dot C parity B dot C. This you can verify later on, maybe in homework. A parity B dot C. This is a bit, okay? Because remember, inner product is always a bit. So this is a bit. But how to get this bit? You can do A dot C. This is a bit. Parity B dot C. This is a bit. Okay? That you can verify. So this becomes xz dot y parity S dot y. Using this formula. Agreed? Now we can see something nice happening. See, let's stick to the case when we are talking about there are two pre-images of every value. In which case, if you think about S is not equal to all zeros. S is some string. Because if S is all zeros, then you are not getting this 2 to the 1 thing, then it's 1 to 1. But let's stick to the case of 2 to the 1. That is, S is not all zeros. Agreed? So now, you see what is happening. If S dot Y is 1, this is 1, so you are getting X dot Y, XZ dot Y flipped. Agreed? Here is XZ dot Y. The 2 will add to 0. Because minus 1 to the whatever, then minus 1 to the whatever flipped. 0. So you will get the probability being 0. If S dot Y is 1. Correct? If S dot Y is 0, you will get, for every such Y, so that S dot Y is 0, each such Y will come out with the same probability. Okay? See, if S dot Y is 1, what happens? You have minus 1 to the something A here, let's call this A, then minus 1 to the A parity 1. A parity 1 is A flipped. A parity 1 is A. So therefore, this minus 1 to the A plus minus 1 to the A flipped will become 0. So therefore, this entire probability will go to 0. That this will happen for every Z, right? Because S dot Y is 1, meaning this will happen for every Z, that this number will be 0. Because it doesn't matter what XZ dot Y actually is. Correct? So this whole thing will be 0. Now, okay? This will be 0. And if you have a Y so that S dot Y is 0, then for all such Y's, the probability that you get the output would be the same. There will be no difference. And the probability will be as it is exactly the total number of Y's so that S dot Y is 0. And that's exactly equal to 2 to the n minus 1. Right? Because you see, S is any particular string. How many Y's are there so that S dot Y is 0? It's exactly half the number of Y's. For any string X, which is non-zero. If S is 0, then for every Y S dot Y is 0. But if S is non-zero, then there are exactly half the strings so that S dot Y is 0. They are orthogonal to S with respect to this inner product. So this is also an inner product actually. If you look at S dot Y the way we have defined, it's kind of an inner product. It's an inner product. So they are orthogonal to S with respect to this inner product. And there are exactly half such Y's. Okay? But anyway, the main point for us is this, not so much this. The main point is that you are not going to get any Y which is such that S dot Y is 1. That you will not get once you measure. Its probability is 0. Okay? Agreed? S dot Y equal to 1 you are not going to get. Its probability is 0. So, what we are going to do, We run the circuit and we obtain a y. Let's call it y1. We know for sure that s dot y1 is not 1. So s dot y1 has to be 0. We know this. Think of s as this s1 through sn. These are the n variables. N variables s1, s2 up to sn. Each are binary variables. You get this equation. Y1 you have obtained. It's a particular string. You have obtained that string. So you can write this equation, right? S dot y1 equal to 0. That is one equation involving these variables. Agreed? S1 through Sn. Again, you run the circuit. Start refresh the whole thing. Run the circuit. Go ahead and measure. You obtain y2. Okay? It is a particular string. Again, it will satisfy this equation with S. This gives you another equation on S. These variables. Correct? Yes or no? Y is getting some value, right? Somewhere it is 1, like the bits of Y's. 1, 0, 0, 1, 1, 0, 0, whatever. That means if it is, let's say, 1, 1, 0, 0, 1, you have S1 plus S2 plus 0 times S3, like that, you write the equation. Correct? You get one equation. You get another equation. Like that, you get n minus 1 equations. Okay. There are n minus 1 equations we will collect. Each time we will run by n minus 1. Now, if we are lucky, and if these n minus 1 equations are linearly independent, you know the concept of linearly independent? Okay. Intuitively it means that each equation is getting some fresh information about S to you. Intuitively, it means you are getting some fresh information about S. These equations are linear. Raise hands who know the concept of linearly independent. Very good. Okay. Linear independent means you cannot get a linear combination of some of these equations to produce the new equation. You cannot do that. So each one of these equations, the entire collection is a linearly independent set of equations. If you have okay, here there are n variables, right? Okay, simplicity, instead of n you think of instead of n minus 1, think of n equations, n linearly independent equations. If you have n variables, n linearly independent equations, you can solve them. Agreed? N variables, n linearly independent equations, you can solve them to find the value of S. Yes or no? That is what you do. So if you are lucky, and if you are actually getting n linearly independent equations, you solve them, get the value of S. Now, what is the probability that you will be lucky? What is the probability that you will be lucky? That means all these n equations that you have obtained are linearly independent. That probability, okay, we can try to do this in one of the tutorials. So the success is when all of them are linearly independent. The probability is at least 1 over 4. So the probability that we are lucky that all these y's that we have obtained are giving us n linearly independent equations is at least 1 over 4. So we can solve for S. Yes, this we will see in one of the tutorial classes, why this 1 over 4 is coming. Okay? Okay? However, when such is the case, So we will be lucky with probability 1/4. So we are going to repeat this process say 4m times. Okay. Yeah, we will see what is the m that is needed. So 1 minus 1/4 is the probability that we will fail in the first trial. What is the probability we also fail in the second trial? Same. What is the probability we fail in the third trial? Same. The probability that we keep failing in 4m trials is at most this much. Now 1 minus 1/4 is 3/4. Okay. Which is at most, so you can do the analysis like there is this thing. One minus x is less than equal to e to the minus x. Okay. So therefore 1 minus 1/4 is at most e to the minus 1/4. 1/4, 1/4 and this 4 will cancel. You will get e to the minus m. Okay. So our probability that we fail in 4m trials is at most e to the minus m. Now you want to make this probability smaller than 0.01, you just choose an appropriate m, which is a constant. Correct? Correct. If I choose, let's say m equal to 20, I get e to the minus 20. It's a very tiny number. I'm happy. Right? That is the probability that I fail in each time. That means the other thing is I will succeed at least once. Correct? Whenever I succeed, I find my value of s. Agreed? Yes. It has a probability involved of succeeding. But you can see that we can easily make the probability very, very close to 1. I choose m equal to 20, my probability of failure is e to the minus 20. A very tiny number. Correct? So this is Simon's algorithm. How many times we are running it? Remember, this is like 20, let us say. Here it is n. Sorry, 80 maybe. This is n. So n times 80. N times 80. Because we have to obtain these n each time, right? No. We collect n equations. We see if they are linear independent. If they are linear independent, we go ahead and solve for s. If they are not linear independent, we throw everything and we restart. 4m. No, because when we collect n equations, to collect each equation, we run that circuit each time, no? You run the circuit once, you get y1. You run the circuit again, you get y2. You run the circuit again, you get yn. This thing, if you do once, you get y1. Then you do again the whole thing, you do it y2. Like that you do n times. Not worst case, this is what you're doing. No, only when you collect n. Then you ask yourself, are these n equations linear independent? You first collect n. Before that you don't stop. Okay? You collect y1, you collect y2, you collect yn. Then you have n equations. Then you ask, are these linear independent? If they are linear independent, you are happy, you go ahead and solve for s. If it so happens they are not linear independent, you throw everything away. You restart. You again collect y1, again collect y2, again. Then you ask, are they linear independent? If yes, you go ahead and solve. If not, you throw away everything, restart. So this will happen at most 4m times. And each time you would be running it n time. So it is 4mn. But m is only a constant, like 20. So 80 n times. Linear in n. Order n. Order n is enough. In the quantum case. Classical randomized exponential in small n. Remember, this is order small n. That one is exponential in small n. Other thing also exponential. Classical deterministic anyway also exponential in small n. So now we can see this difference between linear versus exponential. Yes? Simon's algorithm. See, now you see we are becoming closer and closer to more useful real world kind of problems. And this Simon's problem became inspiration for Shor. The story apparently is that Peter Shor saw this paper and then he got the idea. Because this is some kind of order finding. There is, remember, there is a period here. S is repeating. It's some kind of period finding. Then he connected it to order finding. And from order finding you can go to factoring. So you see how initially it looked like, oh, these are some very simple toy problems we are dealing with. But then you see one thing leads to the other. Deutsch led to Deutsch-Joseph. Deutsch-Joseph led to inspiration for Simon's. Then Simon's is kind of a period finding. Period finding became inspiration for Shor, for order finding. Order finding went to factoring. Yes, somebody was asking a question. Yes.
Different equations.
Yes.
And then we are checking whether they are linearly independent or not.
Yes.
So, sir, when we run it, let's say 2 times,
yes,
to get, let's say, 2 equations.
Yes.
So, like both the equation will be different because we are not changing input. So, what is changing in those two?
No. What we are doing is we run this circuit, we measure, we get y1.
Okay.
Then we keep y1.
Okay.
And throw everything. Restart here. Restart with zeros.
Okay.
Remember, it's all zeros here.
Yes.
Restart with zeros. Do the Hadamard, do BF, Hadamard, measure. Get y2.
So
keep.
But sir, we were doing the same thing to get y1, same thing to get y2.
Yeah. See, you start with zeros. Run the circuit, get y1. Keep y1. Throw away everything. Start again with zeros.
Okay.
Do the circuit. Measure to get y2.
Okay.
Keep y2, throw away everything. Again start with zeros.
N times.
Bits. Yeah. Yes. N bits. Yes. No. No. Sorry. Okay, you're getting confused. Okay, I get it. The bits of y are not the y1, y2. Y1 itself is n bits. For y1, I am meaning the first time you got the y. That is the y1. Okay, I understand this can be confusing. But the point is, by y1 there, what we mean is the first y, the entire n bit y that you got. Then y2 is the second time you ran the entire n bit y that you got. Yeah, not the bits. Any more questions? Now you can see things are getting a little bit more involved also, right? The circuit, the analysis, everything a little bit more involved. But still, hopefully, we are able to follow. At least the math we are able to follow. Meaning, the analysis, each equation, how one is leading to the other, that analysis we are able to follow. Correct? Maybe, developing an intuition about what is happening may take some time. Correct? But at least the math we are able to follow.
Somewhere let s equal to s1, s2 like that it was written. Is
Yes.
It? Maybe that's why I got confused.
Yeah, I got it.
Even y
Yes.
is similarly.
Yeah. Maybe what I should do is instead of y subscript 1, I should do y superscript 1.
Okay.
To
Something
remove that
different.
confusion.
Yeah.
Because s subscript 1 is the bits. Yes, I agree.
Correct.
I agree to that. Because S, yeah, I get it. I get it perfectly well. Maybe I should change this actually. I will call it superscript 1, 2. Yeah, I'll do that. Okay. Okay. Ah. Okay, 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 okay.
Not this part, sir. That probability calculation. No, S dot y equals to 0, not equals to 1.
Yes.
From
yes,
that
yes.
point.
So we are here, right? Okay. So this, till here it's okay, right? Huh? Till here it's okay? Or we should start from here also?
That is clear to me, but second time it's better.
Ah, okay, okay, okay.
Yes.
So we start from here maybe?
Not required, sir.
From here?
Yeah, yes, sir.
From here, okay, okay. All right. So this is the one, okay? Now we are asking probability of output y. If S dot y is 1, we can see that S dot y is 1 here, correct? So xz dot y is some number, let's call it az. It's some bit, agreed? Let's call it az. This is -1 to the az. Okay, let me actually do it here. -1 to the xz dot y plus -1 to the xz dot y parity 1. Agreed? That is the case we are in, S dot y equal to 1. Fantastic. Now let's write it as, remember the formula, remember? The scratching thing is like totally, I'm not able to easily take the scratching. Okay? Now -1 to the 1. Agreed? Remember the formula, -1 to the A parity B is -1 to the A times -1 to the B. Agreed? So it becomes -1 to this, parity 1, -1 to the 1. -1 to the 1 is -1. This number plus this number times -1. And this will happen for all z, right? Because it doesn't matter what this number is. So therefore this will become 0. This will become 0 in case of S dot y equal to 1. S dot y equal to 0, okay, something will happen. But anyway, we can see from the symmetry of things that for any y such that S dot y equal to 0, it will be equal probability. Probability will not differ. We can look a closer analysis, but doesn't matter. I think from symmetry of things, we can believe that for any y such that S dot y equal to 0, it comes out with the same probability. Okay? You see, you can see also, you see, S dot y is 0, okay, that goes away. What is this? -1 to the xz dot y, -1 to the xz dot y. it becomes 2 times. Okay? Agreed? Now, for, okay? Now, what is the, okay? Then there is a summation z here. Okay? Now, okay? So, okay? So now the, okay? So now you can now sum over those z's. How many z's will be there? How many z's will be there?
2 power n minus 1.
Exactly. For any y, so that s dot y, sorry. Totally the total number of z's is 2 to the n minus 1 anyways. Okay. Now, what are we doing? With each one of them, what is the number associated? Minus 1 to the xz dot y. Okay. We do mod square of that. Okay. So basically what you are getting is 2. It doesn't matter whether it's minus 1 or plus 1. Essentially you get 2 so many times. You square and you normalize. You get a number. Okay. Whatever that number is, that number will not depend on y. Agreed? But anyway, the point that it's this, whatever is this value is not even that relevant. What is more relevant is that you're not going to get any y so that s dot y is 1. S dot y equal to 1 has probability 0. You are never going to get s dot y equal to 1. Correct? So the only thing you will get, any y that you will get must satisfy s dot y equal to 0. And therefore you get this equation here. The first y that you get, you run the circuit, you get a y. Let's call the n bit y as y1. The n bit y that you get, let's call it y1. It must satisfy this equation, because s dot y1 equal to 1 is not a possibility. You will not get such a y1 only. Okay? Whatever y1 you get must satisfy this equation. Then you run the circuit again. Whatever y2 you get must satisfy this equation. Like that you keep getting n such equations. You are lucky if all these n equations are linearly independent. Okay? If they are linearly independent, you can solve them to find s. Agreed? Then you are very happy. Now it so happens that you will get at least with probability 1/4 that all these n equations will turn out to be linearly independent. That is a separate analysis to be done, we can do later on sometime. They will turn out to be linearly independent. So with probability 1/4 you are done. With probability 3/4 you will fail. You restart. Again with probability 1/4 you will be done. You will fail with probability 3. Keep doing it. It's like tossing a coin. It turns out to be head with probability 1/4. Tail you repeat. Head turns out to probability 1/4. Tail you repeat. How many times you have to do such that you get one head? Not many times, no. 20 times you do, certainly you will see one head. Correct? As soon as you see head, you have got your set of equations which are linear independent. You go ahead and solve for s. You got your s. Agreed? The bottom line is you are getting these equations. Each time you get a y, you are getting that equation. And you have this collection of equations. And this is also a nice fact that you are going to get n linear independent equations with a constant probability, 1/4. That is important. There are n such equations. But all of, okay, n could be large, n could be a million, a zillion, whatever. But all of them will be linear independent with probability at least 1/4. That is a nice property, right? That you might expect, oh, why should each equation, new equation I get will turn out to be linear independent of the others? But it so happens that that is the case. N of them a million, a billion, a zillion, whatever it is. N could be anything. Independent of that, you will get n equations which are linear independent with probability at least 1/4 of fixed probability. Okay? Not dependent on n at all. So that's the nice thing. And then you do this. Okay? Here, yes. This is inner product, you mean?
Yeah.
Inner product.
Is that bitwise ANDing?
Here is that. Here. A dot B is summation I, AI, BI.
Okay, mod 2 you have
Mod
to
2.
take. Mod 2 you have to take.
Yes. Mod 2. Where? No, it's a number, you see. AI, BIs are numbers, 0 and 1. You multiply, you add, you get a number. Another number could be long number, 12, 13, 14, whatever it is. Then you go mod 2. Okay?
It's basically meaning even, right? The sum will be even.
Hmm?
Sum will be even, that's the idea, right? Mod 2 equal to 0.
Yes, the sum will be even. That's right. And for the analysis of that probability, we are also using this fact, right? The norm 2 square of summation z alpha z ket z is summation z mod alpha z square. This we have seen before. That also we are using. Okay? Any more questions? Any more questions? Good? All right. So we're done with Simons. Tomorrow we'll start 11 with Qiskit. Okay? We'll send you a couple of links. You just install from there. Okay? Even if you don't install, it's okay. I think in the first few minutes you should be able to do it. But anyway, if you can, you do it. Okay? But do bring your laptops. Okay? Does everybody have a laptop? Right? No issues, right? Otherwise, you try to borrow from wherever. Okay?